சார் நீங்க உங்க பேர் சார்?
So myself Pradeep sir, assistant professor from PSNA sir, BME biomedical
உங்க
engineering.
பேர் என்ன சொன்னீங்க?
Pradeep sir, Pradeep.
ஓகே, இப்போ ஒன்னு சொல்லுங்க
சார். சொல்லுங்க.
இப்போ உங்களுடைய உங்க காலேஜ்ல என்ன என்ன டிகிரி கோர்சஸ் ஆஃபர் பண்றீங்க? பிஇ, பிடெக், எம்இ, எம்டெக், எம்எஸ் எது ஆஃபர் பண்றீங்க?
பிஇ, பிடெக், எம்இ, எம்டெக் சார்.
ஓ, எல்லாம் இருக்கு.
இருக்கு சார், நாலுமே இருக்கு சார்.
இந்த பயோமெடிக்கல் இன்ஜினியரிங் டிசிப்ளின் இல்லையா இது?
இது வந்து பிஇ சார். பட் இந்த STTP வந்து ஸ்பான்சர்ட் பை AICT ஃபார் ஃபேக்கல்டி சார். Faculty from various colleges.
That I understand, but
Yes,
unga biomedical engineering programla UG students மட்டும்.
UG students, yes sir, UG students மட்டும் தான்.
இப்போ ஒன்னு சொல்லுங்க, உங்களுடைய BE கரிக்குலம்ல biomedical engineeringக்கு
yes sir,
இந்த மேக்னெட்டிக் ரெசோனன்ஸ் இமேஜிங்னு ஏதாவது கோர்ஸோ ஒரு கோர்ஸ்னுடைய பகுதியோ இருக்கா?
இருக்கு சார், ஷூர் சார். ரேடியாலஜிக்கல் எக்யூப்மெண்ட்ஸ்னு சொல்லிட்டு 5th செமஸ்டர் படிக்கிறாங்க சார், 3rd இயர்ல. சோ அப்ப அதுல வந்து
ஆமாங்க செமஸ்டர், 6வது செமஸ்டர்,
5வது செமஸ்டர் சார், 5th செமஸ்டர் 3rd இயர்ல. அதுல வந்து இதுல MRI வந்து 3rd and 4th யூனிட் ரெண்டு யூனிட் நல்லா பிராடாவே படிக்கிறாங்க சார்.
ஓகே.
MRI and PET CT பத்தி படிக்கிறாங்க சார், பிராடாவே படிக்கிறாங்க.
ஓகே ஓகே
ஓகே.
உங்க காலேஜ் எப்பல இருந்து இயங்குறது சார்?
1984 சார்.
ஓ,
37 years. 37 years complete.
ஓகே, ஐ see. வேற இந்த ஒரே இன்ஸ்டிடியூஷன் தானா இல்ல இந்த குரூப்?
எஸ் சார், சிங்கிள் இன்ஸ்டிடியூஷன் சார், சிஸ்டர் இன்ஸ்டிடியூஷன்ஸ் எதுவும் இல்ல சார்.
எத்தனை ஸ்டூடண்ட்ஸ் இருக்காங்க சார்?
ஓவரால் வந்து லைக் ஒரு 6500 ஸ்டூடண்ட்ஸ் இருக்காங்க சார்.
6700?
எஸ் சார்.
அடேங்கப்பா. அண்ட் பயோமெடிக்கல் இன்ஜினியரிங்ல எத்தனை பசங்க சார்?
பயோமெடிக்கல் எஸ்ஏ வந்து ஒரு 160 இருக்காங்க சார்.
4 இயர்ஸும் சேர்த்தா?
4 இயர்ஸ் சேர்த்து. எஸ் சார்.
ஆவரேஜ் ஒரு ஆண்டுக்கும் 40 பசங்க.
50 to 60 இருக்காங்க சார். 50 to 60. இன்டேக் வந்து 60 சார். ஆவரேஜா 50 to 60 இருக்காங்க.
ஓ, இன்டேக் ஸ்ட்ரெங்த் வந்து 60 இருக்கா? ஓகே.
எஸ் சார், 60.
இதுல வந்து
மத்த டிபார்ட்மெண்ட்ஸ் வந்து மெக்கானிக்கல்ல 360 சார் இன்டேக். மெக்கானிக்கல் 350 சார். சிவில், மெக்கானிக்கல், கம்ப்யூட்டர் சயின்ஸ், ஐடி, ட்ரிபிள் இசி இவங்க 360 சார் இன்டேக்.
ஓகே. அண்ட் இதுல வந்து இப்போ 6700 பசங்கன்னா அதுல பிஜி எத்தனை பேர் இருப்பாங்க?
பிஜி வந்து கம்மி தான் சார், நமக்கு ஒரு 300 ஸ்டூடண்ட்ஸ் இருப்பாங்க சார் பிஜி.
ஓகே. சோ பெரும்பாலும் 6400 கிட்டக்க யூஜி
ஸ்டூடண்ட்ஸ். ஆமாங்க சார்.
பிஹெச்டி எத்தனை பசங்க இருக்காங்க? இப்ப 4 பேர் இந்த மீட்டிங்க்கே வராங்கன்னு சொன்னீங்க.
ஆமாங்க சார்.
எத்தனை பசங்க பிஹெச்டி?
இவங்க வந்து வேற காலேஜஸ் சார். இவங்க நம்ம காலேஜ் யாருமே இல்ல சார்.
ஓகே ஓகே.
நம்ம காலேஜ்ல ஒரு 5 பேர் தான் சார். நம்ம ஆர்கனைசிங் டீம் இருக்கோம் சார், ஃபேக்கல்டி இருக்கோம். எல்லாரும்
எவ்வளவு ஃபேக்கல்டி?
நம்ம 5 ஃபேக்கல்டிஸ் வந்து நம்ம இன்னைக்கு மீட்டிங் போறோம் சார். மத்தவங்க எல்லாரும் மத்த காலேஜஸ்ல இருந்து தான் சார்.
எஸ். இப்போ பயோமெடிக்கல் இன்ஜினியரிங்ல நம்ம ஃபேக்கல்டி எத்தனை சார்?
6 சார்.
6 ஃபேக்கல்டி. ஓகே.
எஸ் சார், 6.
And but you are not offering a PhD program?
Yes sir, we are offering sir, but part time la நம்ம அண்ணா யுனிவர்சிட்டி அண்டர்ல தான் சார் வரோம். நம்ம ரிசர்ச் சென்டர் தான் சார். நம்ம PhD ஸ்டூடண்ட்ஸ் இருக்காங்க சார். நம்ம ஒரு 4
பயோமெடிக்கல் இன்ஜினியரிங்ல இல்லையா?
இல்ல சார், நம்ம
இல்லங்க சார். பிஜி இல்லங்க சார் நமக்கு.
ஓகே.
குட் மார்னிங் சார்.
குட் மார்னிங். யா.
Sir, we'll wait for sometimes, sir, or we'll start,
நீங்க
sir.
எப்படி சொல்றீங்களோ
சொல்றேன்.
அப்படி செய்யறோம். ஓகே,
சரி, okay.
உங்களுடைய முழுமையான கட்டுப்பாட்டுல இருக்கேன் நான் இப்போ.
Okay, sir.
Thank you, sir.
Pleasure, sir. Pradeep, sir, I will start, sir.
ஓகே,
We'll wait for another 3 minutes, ma'am. By
Okay.
9:35 we'll start.
Okay.
Okay.
So 9:35 we'll start, sir.
வாட் எவர் யூ சே மேடம்.
Okay, sir. Okay.
அம்மா என்னுடைய மொபைல்ல கூட.
Sir.
எதுக்கும் இருக்கட்டும். கரெக்ட். ஓ, லபிஷன் அவுட்.
Sudha ma'am, start பண்ணலாம்.
Okay, sir.
Okay.
So we'll start, sir.
Yeah, sure.
Yes. Good morning, all. It gives me immense pleasure to introduce our guest speaker of this morning's session, Dr. N. Chandrakumar, Professor, Department of Chemistry, Indian Institute of Technology, Chennai. Dr. N. Chandrakumar has been with IIT Madras since February 2001, joining as professor. He has established MRI-MRS Center at IIT. Since July 2017, he is Professor Emeritus at IIT Madras. Formerly, he is the Director Grade Scientist at CSIR until February 2001, where he founded Magnetic Resonance Research and Multipurpose NMR and EPR labs from 1982 onwards. He has been a DFG visiting professor at the University ULM, Germany, visiting professor at University Joseph Fourier, Grenoble, France, and visiting professor at Institute for Protein Research, Osaka, Japan. He obtained his PhD chemistry from IIT Kanpur in 1980, MSc chemistry from IIT Madras in 1972, and BSc chemistry with maths and physics from Loyola College, University Madras in 1970 with special distinction. He has more than 45 years of experience, and his research interests are high resolution NMR imaging and microimaging, overhauser dynamic nuclear polarization, double resonance, NQR, spin dynamics, instrumentation, especially hardware and software development for MR. He published more than 100 research papers in reputed journals and published 5 books. He filed 6 patents and granted with 1 patent. His honors and awards are CRSI Silver Medal 2008, J.C. Bose National Fellowship 2009, named lecture awards of the Indian National Science Academy Professor K. Rangadama Rao Lecture 2004, named lecture awards of the Indian National Science Academy Professor R.K. Azundi Lecture 2002, a Millennium Medal in Indian Science Congress 2000. This brief introduction, I hand over this session to Dr. N. Chandrakumar, sir. Welcome, sir.
Thank you, madam. Good morning, and thanks for those kind words of introduction.
Thank you.
Good morning to you all. And
morning,
this session will be an opportunity for me to present to you an overview of the principles and applications of magnetic resonance imaging. Now, I am told that you run a biomedical engineering program at the undergraduate level, and that among the medical imaging techniques or radiology techniques that are covered in your program, in the 3rd and 4th years, you include some MRI as well. So this is probably fairly familiar territory to you all, but let's see how we can wrap it together. And I would be most happy to have your questions anywhere during the talk, anytime during the talk, not necessarily only at the end. This business of magnetic resonance imaging is, in basic science, it is called nuclear magnetic resonance. We drop the word nuclear because magnetic resonance imaging being a radiological technique, and since medical doctors and radiologists will be making use of this heavily, the word nuclear has a different connotation for that community. And that has to do with nuclear medicine, with cancer therapy by gamma irradiation, cobalt therapy, and so on. So it is all about nuclear irradiation. So the word nucleus immediately is connected in the minds of the medical community to nuclear medicine and to radiation therapy and things like that. And this is not what this game of magnetic resonance imaging is. It is about nuclear properties, but it is not about the radioactive decay of nuclei, which results in the emission of gamma rays or beta rays or alpha particles and so on. Those are high energy processes, but here we are talking about just the magnetic moment of the nucleus. Several isotopes in the periodic table of elements have magnetic moments that are non-zero. And the business of nuclear magnetic resonance imaging or simply magnetic resonance imaging, when you drop the word nucleus for the sake of the medical community or the radiological community, is just about the magnetic properties of the nucleus and imaging modalities based on this. Now, the first person who discovered and measured the nuclear magnetic moment was Otto Stern. He did this with a sample of orthohydrogen, which is just a hydrogen molecule with both the proton nuclei having the same spin state, let's say, both parallel spins. Okay. And he was the one who was the first one to measure the nuclear magnetic moment. This was almost 90 years ago. And then one of his former students, come postdoctoral fellows, Rabbi, found a more efficient method of measuring magnetic moments, and this was the so-called resonance method. So you will recognize that the moment we say that a nucleus has a magnetic moment, then this acts like a magnetic dipole, which has, of course, a north pole and a south pole. Now, magnetic resonance implies that you are somehow flipping the poles of the nuclear dipole. The magnetic dipole of the nucleus is flipped. Okay, originally, if the north and south poles have a certain orientation, let us say the north is pointing up and the south is pointing down. Then, by some means, if you're able to flip the orientation so that the south is pointing up and the north is pointing down, this is what resonance is all about. So resonance flips the poles of the magnetic dipole, and in consequence, you're able to measure an electromotive force in a suitable instrument. Okay, so how is this managed? How do you manage to flip the poles of the magnetic dipole moment? This is done by using resonant electromagnetic radiation. So when you have nuclear magnetic moments in an external magnetic field, the nuclear magnetic moments precess around the external magnetic field with a characteristic precession frequency. The precession frequency is characterized by the strength of the magnetic field that you're applying, called the Zeeman field strength, and also characterized by the magnetogyric ratio, or the so-called gyromagnetic ratio of the nuclear isotope in question. So the precession frequency is a function of the magnetogyric ratio, or the so-called gyromagnetic ratio, as well as the field intensity. Now, since these nuclear magnetic moments are precessing around the Zeeman magnetic field at this precession frequency, if you irradiate the system of nuclear magnetic moments inside this magnetic field with electromagnetic radiation of the appropriate frequency that matches the precession frequency of the nuclei, then you get resonance, and you're able to flip the poles of the magnetic moment. The orientation of the magnetic dipole is flipped. And then you can measure an EMF in a suitably wound coil in the instrumentation of the experiment. And the people who took this forward, starting from Otto Stern 90 years ago, and a few years later, Rabbi, who had initially associated himself with Stern and then did his work independently. After this, these guys were working with atomic beams and molecular beams. So they measured nuclear magnetic moments at low temperatures and low pressures or high vacuum using beams of atoms or beams of molecules, but not bulk matter as, let us say, even a gas phase at a reasonable pressure, leave alone a liquid or a solid. And Bloch and Purcell, they were the first to independently demonstrate that nuclear magnetic resonance could be achieved in bulk matter, let us say in a sample of liquid water or in a sample of the soft solid like wax, candle wax and things like that. So these two people were the first to show that you can get, in bulk matter, you can measure the nuclear magnetic resonance. And this was then put to great use by the new techniques that were invented by my honored Nobel laureate, whom I am privileged to count as a personal friend, Richard Ernst. He showed that these properties of nuclear magnetism in bulk matter can be used to find the structure and the dynamics of molecules and to study the interaction between drugs and proteins or drugs and membranes and so on. And later, partly in collaboration with Richard Ernst and partly independently, another good Indophile friend, Kurt Wüthrich, did a lot of work determining the structure of proteins by nuclear magnetism. But this is nuclear magnetic resonance spectroscopy. But then you see that Peter Mansfield and primarily Paul Lauterbur, more or less simultaneously and independently, they invented the technique of magnetic resonance imaging. Okay, and that is the subject of this talk. Now, why are we interested in this? After all, we are familiar with many different kinds of imaging and microscopy techniques. X-rays can give you images of crystals with even atomic resolution. Similarly, you can use transmission electron microscopes, scanning electron microscopes, nowadays scanning probe microscopes of one kind or the other to get you images of surfaces primarily with some depth resolution at a kind of atomic or molecular resolution level. You can use ultrasound for imaging as well. But then why are we interested in MRI? One of the reasons that we are interested in MRI is basically magnetic resonance imaging is not a genuine imaging technique at all. A genuine imaging technique, I'm putting this word genuine in quote unquote genuine, okay? Or we should say a traditional or a conventional imaging technique is about the scattering of the relevant radiation from the object that you're trying to image, or the diffraction of the relevant radiation from the object that you're trying to image. Whether you're talking about X-ray diffraction or electron microscopy or ultrasound or any other comparable technique for imaging, these are all based on the conventional method where you allow a beam of rays of some wavelength to fall on the material object that you're trying to image, and then these rays get bounced off from the object, and then you can recreate the image of the object. This is not the way MRI works. As a consequence, as you know, for the business of diffraction or scattering and so on, optimal results are obtained when the incident beam is essentially perpendicular to the object that you're trying to image. And so you get an axial or a so-called transverse image. But NMR is not like that. MRI can produce images at any arbitrary orientation. And here we are showing you a coronal view of the human brain. Imagine that you're wearing headphones as you're speaking, and the plane of the headphones, you know, the plane through the head, which includes the headphones, is what you can identify in your mind as the coronal view. And whereas you can get primarily a transverse or a so-called axial view by using most other imaging techniques, you can get a coronal view by MRI, you can get a sagittal view from MRI, right, which is the plane including the ear lobe, right? And you can get, of course, the transverse of the axial view. What is more, you can get any intermediate view between the three orthogonal views, namely transverse or sagittal or coronal. You can get any oblique view. For example, when you want to do cardiac imaging, this is of relevance because, of course, the heart is not lying in the plane of the chest or the thoracic cavity. It is slanted, okay? And it is at an oblique plane, which is it's not a vertical or a horizontal plane of one or the other orthogonal orientation. With respect to the thoracic cavity or with respect to the chest, the heart is at an oblique angle. And you can do oblique imaging, right? So one of the main reasons we do MRI is because we can get arbitrary views of the object. You don't have to hang up your object at various angles to get arbitrary views. You can get arbitrary views just like that. Now you can see the coronal view of the human brain. For those of you who are interested in the biological aspects of the story, you can see various structures in the brain are well identified here. And this is another unique strength of MRI, the soft tissue contrast. So here you see the corpus callosum, the fornix, the internal cerebral veins, the third ventricle, and so on. and also the body of lateral ventricle, the thalamus, the lateral cistern, and the insular cistern, and so on and so forth. You can read all the structure which is included in this coronal view of the human brain. And that is another unique strength of MRI. X-rays, for example, are exceptionally good at dealing with hard matter like bones. They can produce excellent images of bones. But the soft tissue imaging capability is a unique strength of MRI. So these are two important reasons that we find MRI so useful for all kinds of investigations, whether they be into the materials imaging context or the biomedical imaging context. One is the ability to generate arbitrary views of the internal structure and the internal dynamics of objects, and the other is the enormous soft tissue or soft matter contrast capability. Okay. Now, as other examples of this, however, the dynamics which I mentioned, so it's not just anatomy, it is physiology also, or the dynamics. So here you see an example of a functional magnetic resonance image. Now, the brain, of course, doesn't have these colors like yellow or light green or whatever, which are shown in this image. As you know, in computer graphics, you can always set up a color lookup table or a CLUT in order to give a 8-bit or up to a 24-bit color coding of the image that you have produced. The colors are randomly chosen by you. It is not a reflection of the true color of the tissues in the brain, but it is just a handy way of visualizing. Okay, so in colors which are pleasing, many radiologists prefer the grayscale, but many others, especially for aspects like functional magnetic resonance imaging, they use a color lookup table for their 8-bit to 24-bit color lookup table for rendering the images. These colors are just computer generated. But the important thing is, you see in these 4 images, the top 2 and the bottom 2, that there are certain portions which are kind of yellowish or brightish in view, as compared to the background, which is like darker. And so you can say that some portions of the brain have lit up, as it were. And these are the portions of the brain which are active in the performance of certain specific tasks. So if you are snapping your fingers, this snapping of fingers and the muscular action which allows you to snap your fingers is all controlled by certain regions of the brain. And in functional MRI, you're able to map which regions of the brain are mapping what function. If I'm speaking now, then I use my larynx finally, but everything that we do is controlled by the brain. And if I'm speaking, the speech areas of the brain will be activated. And functional MRI will allow you to see which are these areas which are working. And this becomes very useful, not only in basically mapping the various regions of the brain with respect to their function, but also in the cases of differently abled people or people who have suffered brain damage of one kind or the other, where nature is so clever that adjacent areas of the brain that are next to the damaged portion will gradually start taking over partially the functions of the damaged region. And you can see all this by functional MRI. Okay, and functional MRI typically works on the basis of producing an image contrast. Whether you saw that anatomical coronal view of the brain in the previous slide or now this functional MRI, this is again the great power of MRI, the contrast capability. As I said already, the soft tissue contrast, okay? And this contrast in functional MRI is mostly controlled by the blood oxygen level in the brain. So when you perform a task, the blood oxygen level varies, okay? The oxygen in the blood is used up in providing energy for the brain processes. Fresh flow of blood into that functioning part of the brain occurs through the microcapillaries there. And then you see that the image is going to show up the fact that now there is a oxygen deprivation followed quickly by a fast replenishment of the blood flow. So the blood flow characterizes the functioning of the brain in different locations for performing or controlling different tasks. And this blood oxygen level dependent contrast is the basis of functional MRI. Now, We can use MRI for various other things. It is not just for clinical work or biomedical work, although this may be of direct relevance for your program and for your interests, but we can use it for a variety of other things. Now, we will talk about how we produce these images in some detail as we go along. But here you see, we tried to map the image of a hydrogen, oxygen, proton, electrolyte membrane fuel cell. Now you saw in a fuel cell of this kind, the PEMFC, proton electrolyte membrane fuel cell, you feed hydrogen, let's say from the anodic end and the oxygen from the cathodic end, and the hydrogen becomes a proton, crosses the electrolyte membrane, and then combines in the cathode region with the oxygen which is coming in there and forms water. So, H2 plus half O2 gives rise to H2O plus energy. Now, in the context of this electrochemical environment, the energy that is released in this chemical reaction comes out as a voltage, and you can connect a load across this fuel cell, and you can draw a current, and you can run your device. And the thing is that sometimes these are all sealed units, like batteries, the fuel cells are also sealed units. Now, what is going on there is a simple reaction. Okay, H2 plus half O2 giving rise to H2O, but you keep supplying the hydrogen and the oxygen from the two ends of the fuel cell. Nevertheless, suddenly you will find that the voltage drops. Now, what is going on? It's very difficult to find out because this is a sealed unit. The MRI allows you a unique window to peep into the sealed unit and find out what is happening. Is the water getting formed? More important, is the water that is formed draining out? Because you see, all chemical reactions are effectively equilibrium processes. They can go from left to right in the forward direction. They can also go from right to left in the reverse direction. But of course, you need the forward reaction to keep going on to produce a voltage from the energy released when water is formed. So if water is allowed to accumulate, this forward reaction from left to right will not go and the voltage will not form. Voltage will be dropping. Energy is no longer released because the reaction is not going on. Now the reverse reaction, if you provide energy, the reverse reaction will go on, and that is the electrolysis of water to produce hydrogen and oxygen, right? So you're not giving a voltage, you're generating a voltage, but the voltage generated can drop to zero if the water is not drained, because the equilibrium reaction will stop happening if the product is not continually removed. And we can map all this. We can see what is happening to the water. So please remember in those previous slides also, what are we mapping here? We will come to that. Okay, what are we mapping? It's mysterious, isn't it? Because here I have now broken the mystery a little bit. Okay, this is a hydrogen oxygen fuel cell. Hydrogen and oxygen gases combine to produce water, liquid water, and at room temperature, at ambient conditions, and produce a voltage. Okay, and you can see whether the water is being drained properly, is it managed properly in the fuel cell by using MRI. What about other living objects like plants? Okay, you know that all of us, whether it is animal kingdom, human beings, or plants, we depend on the flow of nutrients for maintaining the life processes. Okay, if the nutrient flow is stopped, then life stops. And here we show that MRI, and sometimes we call this MRM, magnetic resonance microimaging. I will explain why we call it microimaging later on. Okay, we can study the flow of nutrients, for example, in a plant, okay, by suitable radio frequency hardware in which the plant is put in and the whole assembly is put inside the magnet. Okay, we'll not go into the details of this. Plant is very clever because it's able to make its own food. நம்ம ஒளிச்சேர்க்கைன்னு கேட்டிருக்கோம் இல்லையா, photosynthesis, where in the presence of sunlight, the plant is in its green leaves, which have chlorophyll. The plant is able to convert water, which it may absorb from the soil and comes up through the roots, right up to the leaves. Okay. And that water combines with the carbon dioxide in the atmosphere to produce sucrose. And the sucrose is then transported down the vasculature. Like we have blood vessels, there are vascular bundles, the xylem phloem system of plants, and we can map those. The xylem phloem structure is what is shown here. Now, these are complicated experiments to perform. And you have to have a variety of radio frequency excitation and detection strategies which you can develop. If you are smart and if you are developing new strategies, they are patentable, maybe you can win some money. And in fact, the guys who invented magnetic resonance imaging, Paul Lauterbach and Peter Mansfield, whom I referred to earlier, both won Nobel Prizes, but they also had patents, which probably gave them much more money than their Nobel Prize money. Okay, so there's a lot of radio frequency excitation detection strategies that need to be optimally designed for MRI experiments, hardware and software for radio frequency work, and that is also a money spinner. You can look at how other processes take place in something like ஒரு சாத்துக்குடியை வந்து பறிச்சுட்டு எப்படி பழுக்கிறதுன்னு பார்க்குறோம்னாக்கா we can find out from the molecular fingerprint of the fruit ripening process. Here you produce the image of the object in 3 orthogonal views. That is the interior of the satukudi or the sweet lime. And now you can take a spectrum which gives you the molecular fingerprinting of whatever is inside the satukudi. Now, of course, the sweet lime, like all the fruit, they have a fair amount of water. But now we are not interested in the water. Like we were interested in the plant case, not in water, but in sucrose, right? Similarly, here, in the case of the fruit ripening, we are not interested in the water. We are interested in a whole lot of metabolites like citric acid, sucrose, glucose, fructose, alanine, various other amino acids, and various kinds of sugars. And we can map all this from chosen regions of the fruit without cutting the fruit or juicing it. The fruit is intact inside your MRI scanner. You do a more specialized experiment than MRI, which is now called MRS, or magnetic resonance spectroscopy, volume localized magnetic resonance spectroscopy. Then you get a so-called high resolution spectrum, which gives you the molecular fingerprint of all the molecules that are inside that sweet lime. And thereby you can monitor processes like the ripening of a raw fruit. பச்சையாக வந்து காய் வட்டா அந்த சாத்துக்குடி இருக்கும்பொழுது புளிப்பு இருக்கும் இல்லையா, so you get the citric acid. As it ripens, it becomes sweeter, no? So you see that this sucrose, glucose, fructose content will improve, and you can map all this and track this as a function of the number of days. And you can find out the concentration of the various constituents, citric acid, sucrose, glucose, fructose. There's even some alanine, ethanol, choline, methanol, and so on. You can find out. You can do this in the brain of human beings or small animals. Supposing somebody has suffered a brain stroke, okay, then the oxygen supply deprivation takes place in that region of the brain where the stroke has occurred. And if oxygen supply is stopped in a certain region of the brain, then the metabolic processes are taking place in the absence of oxygen. This is called anaerobic metabolism. Now, for the brain processes to occur, you need energy, and that is provided usually by the glucose. The glucose is able to cross the blood-brain barrier, okay, and it provides the energy for the processes of the brain. When you think and control actions and so on, you need energy, and that is provided usually by the glucose in your blood, which crosses the blood-brain barrier and is metabolized in the blood. It is burnt in the oxygen, right, to produce carbon dioxide and water and energy. So these are all chemical reactions. It's like a fuel cell again, okay, but a different kind of fuel cell. This is not oxygen and hydrogen, okay? It's not hydrogen burning in oxygen to give water. Burning without a flame is a soft chemistry, enzymatic processes, okay? You don't require high temperature, you don't ignite something and so on. In the body, you cannot afford to ignite anything, right? So these are taking place under physiological conditions, okay? 98.4 degree Fahrenheit or the corresponding Celsius scale, and it's all deuce, shimmy deuce, soft chemistry. But in the case of brain processes, glucose plus oxygen gives carbon dioxide and water and energy. Just like in the fuel cell, hydrogen plus oxygen gave you water and energy, right? And if the metabolism becomes anaerobic, you don't get carbon dioxide, you get lactic acid. So this is important. Somebody has suffered a brain stroke and you want to see what has happened to his metabolism. You're not content to just see the image. The image will show up whenever there is a stroke. Usually there is a lot more water in that region of the brain tissue, which has suffered a cut in the oxygen supply, which has suffered the stroke. I think it's called aneurysm or something like that, technically, in the biomedical parlance. So you have this problem there, let us say, or edema, I'm sorry, edema. Okay, there's an accretion of extra water there. And you can image this with the MRI. But when you go further into this and take the spectrum from a portion of the brain, you're not dissecting it. Huh? It's completely non-invasive and non-destructive, whether we're talking about MRI or MRS typically. But you're able to not only get the image based on the water distribution and the water mobility in portions of the object that you're trying to image, but you're also able to look at the various molecular soup, constituents of the molecular soup in the brain or in whatever organism you're looking at. Here we have the evidence of anaerobic metabolism and the production of lactate, which you see as two blobs on the top and the bottom in this two-dimensional spectrum. Okay, and this shows you that the metabolism has become anaerobic. So if you give therapy to a patient or to this animal which has suffered a stroke, then gradually the brain processes will be restored if the system is not brain dead. And when the brain processes are gradually restored, the metabolism becomes aerobic again. Lactate is no longer produced because it's not anaerobic metabolism, and you get carbon dioxide and water, and the lactate signals will disappear. So you can monitor therapy and the improvement in the patient's condition by using this kind of experiment, which is called MRS. Now, of course, there are a lot of medical imaging techniques like X-ray CAT scans, ultrasonics, positron emission tomography, and MRI. And I think one of your colleagues whom I was speaking to a few minutes before this talk mentioned that in the 3rd and 4th years of your radiology course, if I remember right, he said you cover both positron emission tomography and MRI. I hope I am not misquoting him. But as I have already mentioned to you, there are a lot of advantages to using MRI. And the instrumentation wise, there has to be a source of radiation, and there is a so-called place where you put your sample, and then there is a detector. This is how the instrument would look like: the radio frequency and the magnetic field controlling hardware in the 3 racks on the left, and the magnet itself in this vertical bore system, which is shown on its own here in a tighter view. All right. And here is something which is more similar to the conventional radiological MRI system: the electronics which produces the radio frequency excitation and the magnetic field gradients and magnetic field control systems. And the magnet itself is much more like the MRI systems in clinics. This is still not an MRI system which is good for clinics because it has got a clear bore of only 40 centimeters. And the largest object that you can image in such a magnet will have a diameter not exceeding a little bit less than 20 centimeters. That's not good enough for imaging an adult. So this is not an MRI magnet, but of course it's in my lab and we don't do medical work. So we do small animal work occasionally, but more characteristically, we do materials imaging, fuel cell imaging, membrane imaging, and so on and so forth. And we also do occasionally some little bit of plants and animals. Okay, no human work. So this is the kind of magnet of MRI scanners, except that it may have a bore of 70 or 80 centimeters instead of 40 centimeters. This one is a 4.7 Tesla magnet, but the FDA regulations tell you currently, I believe, you're not allowed to go beyond 3 Tesla for clinical MRI. But for experimental purposes, even if you are doing human work with the informed consent of volunteers, people are going up to even 11.7 Tesla. But that is not allowed by FDA for routine clinical work. For routine clinical work, you do not go beyond 3 Tesla magnetic field. So here are the important constituents of the MRI system from the point of view of the instrumentation. First of all, there has got to be a magnetic field, which we call as the Zeeman magnetic field. There has also got to be a chamber in which you will place the object that you're trying to image. It's a human for biomedical or clinical purposes. It can be a fuel cell or a plant or a small animal for our purposes, or whatever you want to image. So you must have a structure in which you can place the object to be imaged and put that whole thing inside the magnet bore. And now that structure in which you place your object to be imaged is part of a tuned circuit which is tuned to the appropriate radio frequency waves. Because now the next thing is you got to have a source of radio frequency radiation okay? And you irradiate, as I said, the resonance process has to be set up so that the magnetic poles of the nuclear magnetic dipoles can be flipped around, okay? That is how you get the EMF induced in your resonator. And what is going on is the nuclear magnetic moments, which are visualized on the surface of the cone on the left, with the magnetic field shown by the vertical arrow here, right in the middle. The slanting arrows on the surface of a cone represent the nuclear magnetic moments, and they are distributed in equilibrium conditions. They're distributed uniformly on the surface of the cone. This corresponds to two possible orientations, let us say, of the proton nuclei of water. The orientation corresponding to this cone, where the nuclear magnetic moments all have a non-zero component parallel to B naught, and that is called the plus orientation of the nuclear magnetic moment. And then you have another possibility for the proton nuclear magnetic moments of water. You have the minus orientation, where you should visualize another cone which is pointing below. Okay, just imagine you have a mirror. If the B naught is considered to be in the Z axis, imagine you have a mirror plane in the XY plane and reflect this cone in the bottom, in the mirror plane. You get another cone which is pointing down. And all the magnetic moments which are distributed there will be called as having a component along B naught which is opposed to B naught, and that's called minus. But actually in water there are two protons, so the two nuclei each can have a plus orientation or a minus orientation. Obviously you will have four possible pair orientations. Both are plus or both are minus, as in the top here, or one is plus and the other is minus. And which one is first and plus and which one is minus gives you two possibilities. Okay, so what we are doing in MRI, once again to recapitulate, we are putting the object whose image or whose MRS we want from chosen portions of the object. We're putting this in a magnetic field, and we are enclosing this typically in a resonant structure, which we may call as a resonator. And this resonator is connected to a source of radio frequency irradiation, and the spectra are obtained. The spectra is just a resonance frequency. Okay, the spectrum is just a name for the set of resonance frequencies. Because what happens is there is not one unique resonance frequency which is able to flip the poles of the nuclear magnetic moment. In a typical molecule, you may have many closely spaced resonance frequencies. For example, different protons of alanine or water or sucrose or glucose or fructose, okay, or citric acid. They would all have small differences in their radio frequency resonances. If the resonance frequency is 100 megahertz, the resonance frequency differences, which are called chemical shifts, may be of the order of 10 parts per million. So in 100 megahertz, 10 parts per million is 1 kilohertz. So you may have a spread of resonance frequencies over a band of about 1 kilohertz at a resonance frequency of about 100 megahertz if you're dealing with the proton NMR spectrum. And that comes up from this frequency equation, that the resonance frequency, which we have called here as omega naught, is minus gamma B naught, where gamma is the magnetogyric ratio and B naught is the Zeeman magnetic field intensity. But now to produce an image, we have, look at the equation right at the bottom, we have the second term within parenthesis, and this is the term G dot R. G is a gradient vector which has an X, Y, and Z gradient. This is a gradient in the B naught field. And the B naught, by convention, of course, the magnetic field, it has a fixed orientation. It's a static field. And by convention, we take the orientation of the B naught field to be Z. So the gradient is the variation of the field along Z, but this variation can be as a function of X coordinate or Y coordinate or Z coordinate. So the variation of the field along Z with respect to the X coordinate is called the X component of the gradient, right? The variation of the field along Z with respect to the Y coordinate will be called the Y component of the gradient. And the variation of the field which is in the Z direction, its variation with respect to the Z coordinate will be called the Z gradient. But they're all variations of the field which is taken to be along Z. But the variation of this Z field can be with respect to X or Y or Z coordinate, right? Or any arbitrary coordinate in between, if you don't want to use the Cartesian system of coordinates. And R is a position vector of any point in the object. So you say that the resonance frequency, which should have been just governed by the magnetogyric ratio gamma and the magnetic field intensity B naught, this is what I told you earlier, that the resonance frequency is a function of the gyromagnetic ratio gamma and the magnetic field intensity B naught. But now you see you have produced a gradient which is uniform over the object, hopefully. And the gradient vector is the vector G. And this produces an additional field at every point within the object. And this field is given by the dot product of G with the position vector of that point. So the total field is now not B naught, but it is B naught plus G dot R. And this field is all taken to be along the Z direction. And that is now the modified equation for the resonance frequency. Omega naught is now not just minus gamma B naught, but there's a second term minus gamma G dot R. And so you see that the resonance frequency becomes a function of the coordinates at which, let's say, the water molecules are located inside the object that you're trying to image. And that is the secret of MRI. In any biological object, you have 70% minimum guaranteed amount of water. If it is a living biological system, that's a minimum guaranteed amount on an average, 70% water. Okay. Now this has a certain resonance frequency, omega naught equals to minus gamma B naught for the proton nuclear magnetic moment. But this magnetic field B naught is supposed to be very uniform or homogeneous. That means it has hardly much spatial variation. Now you go and deliberately generate a gradient. That means you generate a spatial variation of the field by introducing new gradient coils, which are anti-Helmholtz coils of one kind or the other. Whereas the field may be produced, the homogeneous field may be produced by a solenoidal coil or a Helmholtz coil. You can produce gradients by using, let's say, anti-Helmholtz coils. Okay, and you supply a current through those gradient coils, you produce a gradient which is superimposed on the main magnetic field, which is homogeneous. Okay, so you see that the resonance frequency becomes a function of, let us say, the position of the water molecules in your object that you're trying to image, and that gives you the map of the spatial distribution of whichever molecular species whose distribution you're trying to image. Typically in biological objects and by default in MRI, you're simply mapping the distribution of water. We have already come across some exceptions. I have shown you how we in our lab with some European collaboration image the distribution of sucrose in living plants. We've shown you how we could produce the MRS, volume localized molecular fingerprint from within chosen regions of an object, like in a fruit or in a rat brain and so on. But the default, okay, for MRI is just use the water molecules which are present to at least 70% of any living biological object and just map their distribution and mobility as a function of spatial coordinates. And the key is that the resonance frequency omega naught, which should be a function of only gamma and B naught, now additionally becomes a function of G dot R. And G is under your control. It is the gradient that you are producing. Mind you, B naught is also under your control. It is a magnetic field that you have produced. But that magnetic field is persistent, it is static, it is a DC field. But we will see later that the gradient that you generate, hopefully you will be able to switch it, you will be able to pulse it, you will be able to rotate it, and you will be able to change its amplitude very rapidly within time scales of the order of milliseconds. The main magnetic field may be 1 or 3 or even higher number of Tesla. There's no way you can switch it rapidly, and the MRI experiment doesn't switch the main B naught field at all. But you can switch the G gradient. And that switching time It's a very small gradient. For MRI, you might use maybe about 5 Gauss per centimeter as the gradient amplitude, right? So that is a very, very small kind of gradients that you will use, 5 Gauss per centimeter. Or you can say, you can convert that into Tesla per meter also, right? 5 Gauss per centimeter, you can convert it to Tesla per centimeter meter, okay? But this is the typical order of magnitude. 5 Gauss per centimeter is a gradient field. You can switch this in the order of a millisecond. And the gradient is written down in this form, okay? The vector G is the unit vector along x times the spatial variation of the field along z with respect to the x coordinate, keeping y and z coordinates fixed. And similarly, the y component of the gradient and the z component of the gradient. And then you have this frequency encoding of the spatial coordinate. Okay, the spatial coordinate R is encoded into the precession frequency or the resonance frequency of the nuclei. And so you see that not only is the frequency a function of minus gamma b naught, it now has the second term in square brackets minus gamma times x times dB naught by dx at constant y and z plus y times dB naught by dy at constant z and x plus z times delta b naught by delta z at constant x and y. That is the secret to imaging. Now, of course, if there is a frequency encoding of spatial information, if you let this frequency difference, which depending on the coordinate difference, if you let the frequencies evolve in time, then you get a phase shift. And of course, as you know from elementary considerations, a phase is just time integral for time dependent frequency. So this is what you measure in MRI. You measure frequency shifts of the precessing magnetization of the nuclear spins, typically by default of the water proton nuclei. And you also measure not only the frequency shifts, but in principle, the phase shifts. But the phase shifts are nothing very different from frequency shifts. They are just the time integrals of the frequency shifts that we talk about. So this is what MRI is all about. It's a measurement of the frequency or phase shifts producing the desired spatial information because the frequency encodes for the spatial coordinate and therefore the phase encodes for the spatial coordinate. Okay. The unique features of MRI is that it is non-invasive and non-destructive. Now you would know that sometimes we use contrast agents in the MRI business in clinical biomedical work. But I would say 90% of the time, this is not necessary. Sometimes, it's not a nice thing to say, but sometimes the contrast agent may be used just for commercial reasons. Because I could safely say at least 2/3 or 3/4, if not 90% of cases, you don't need to administer an exogenous contrast agent like a gadolinium complex with DTPA or anything like this. Gadolinium is one of the popular rare earth ions which are complexed with certain ligands like DTPA and so on. This is a popular contrast agent. There are dozens of them now. At least 2/3 to 3/4 of the time, if not 90% of the time, an exogenous, externally administered contrast agent is not required because the unique feature is there is an inherent contrast capability that is built into MRI. This is very different from what we do in microscopy. For example, in optical microscopy, you have to use a staining agent, right? So you have to do this kind of a thing, slicing or microtoming or ultra microtoming for optical microscopy, for electron microscopy, and so on. Nothing like that is required here. We use a slice imaging here also, but there's no microtoming. We choose a notional slice from the brain without cutting the brain. Just by using radio frequency waves with a magnetic field gradient appropriately, we can choose the region of the brain that we will image. And we say we have picked out a slab or a slice of the brain for imaging, but we have not really physically sliced it or microtomed it. This is very different from optical microscopy or electron microscopy. Okay? You have to do a microtoming or ultra microtoming for those other techniques. And then you got to fix the sample. and stain the sample. You don't need anything like this. Okay, the contrast is typically at least 2/3 or 70%, if not 90% of the time, the contrast is inbuilt into MRI. It is endogenous contrast. Exogenous contrast is not often required, but it's very often administered, I'm afraid, partly for commercial reasons. Okay, as I said, however, by and large, it's a non-invasive and certainly a non-destructive technique. If you administer a contrast agent, you might say, okay, I've invaded this material by administering the contrast agent. Okay, exogenous contrast material, so I've invaded this. Okay, but typically you don't need it, and then it is MRI is both non-invasive and non-destructive. You can get a one-dimensional image, you can get a two-dimensional image, you can get a three-dimensional image also. All the three spatial coordinates can be imaged, or just one of them or two of them. Any arbitrary axis for the imaging for 1D and 2D images. Spectral spatial imaging, you can combine the spatial information with the spectral resonance frequency. So you can have 4 or 5 or 6 dimensional data sets where 3 dimensions are the spatial coordinates up to 3 dimensions, and another 1, 2, or 3 can be the spectral dimensions where the different resonance frequencies which are dependent on the molecular structure show up as a molecular fingerprint or as a chemical shift. So you can have a spectral spatial imaging where you get both the spatial and the spectral information along orthogonal dimensions of a multidimensional data set, and contrast is inherent to MRI. The contrast can depend on the density of spins. This is called the PD image, or the proton density image. Just how much water is there in a given region of the brain. That's a PD image of the brain. Or the mobility of the water molecules which you are imaging by default. And the mobility can be reflected in something which we will see is called the relaxation time of the nuclear magnetic moment. And there are two kinds of relaxation time. One along the magnetic field direction, which is the time constant T1, and the other is perpendicular to or transverse to the magnetic field direction, which is called the T2. So there are these two different relaxation times. It can depend on the nuclear isotope, it can depend on the molecular or the chemical shift. The contrast can also depend on diffusion or flow. So you got all kinds of things, but how about the resolution? The resolution is only about as good as optical imaging. It is nowhere near as good as the atomic resolution you can get by X-rays or by electron microscopy or by atomic force or scanning probe microscopies. It is as good as ultrasonics, it's as good as optical imaging at best. But then who needs better resolution for the biomedical context? You don't want to see single atoms in the biomedical imaging, and the resolution is of the order of, let us say, about 10 microns. But please remember, what is the wavelength of the rays we are using? You can calculate this by using the relation nu times lambda equals c. Frequency times the wavelength is the velocity of light. And if the frequency is 100 megahertz, you can calculate what is the wavelength. You can say typically the wavelength is of the order of a meter. Now you see the wavelength of the radiation we are using is a meter, but the resolution we can get is down to about 10 microns. That is what I said right in the beginning, that this is not a scattering or a diffraction technique where the image resolution is primarily a function of the wavelength of radiation that you employ. Image resolution is limited in conventional imaging by the wavelength of radiation that you use. It's only in the last 5 or 10 years that people have used nanoscopy by fluorescence, going down to resolutions which are better than the optical wavelengths that are used. But in MRI, we have been doing this for 50 years. 1 meter wavelength of radiation, 10 micron resolution, because we don't depend on scattering or diffraction at all. So our image resolution is not limited by the wavelength. It's essentially primarily independent of the wavelength. And it depends on the gradient amplitude that we use, which encodes the spatial information by frequency variations in the object or phase variations of the magnetization in the object. It also, the resolution is determined by the sensitivity of your EMF. How much signal to noise ratio you can measure in the EMF induced, per volume element. And it is also limited by molecular diffusion. Because these is soft matter we are talking about, And it is about imaging the spatial distribution and the mobility of water. But water molecules will not stay rooted to a spot or pinned to a spot. They are moving around by Brownian motion, random motion. And if you say that the diffusion coefficient under ambient conditions is of the order of 10 power minus 9 meters square per second, then you see that in about a millisecond of the image encoding time, the RMS displacement of the water molecule itself is about 1.4 microns in one dimension, which means your image resolution can never be better than a couple of microns at best. That's why we say that usually in three-dimensional case, it becomes 6 times dt, so it becomes 4.2 microns. So you'll say about 5-ish microns. That's why I said the resolution cannot really be significantly better than about 10 microns. Okay, so it is limited by the gradient amplitude, by the EMF signal to noise ratio that we pick up in detecting the resonance signal, and by the molecular diffusion or the so-called self-diffusion. We have many different approaches to MRI. There is Fourier imaging, there is projection reconstruction imaging, and there is echoplanar imaging. Now, the projection reconstruction imaging is much like X-ray CAT scans. In fact, when Hounsfield got the Nobel Prize for X-ray CAT scan, which is pioneered by him, he devoted half of his talk to just the upcoming method, which had just been invented by that time, MRI. He had invented X-ray CAT scanning, but half his Nobel lecture was devoted to the new technique, which was just then upcoming from other laboratories worldwide of MRI. But the projection reconstruction approach, which is what the first MRI experiments used, is taking a leaf out of the X-ray CAT scans. Use the same philosophy for imaging. Okay, you use a gradient, acquire the resonance signal. Then the gradient is constant. Acquire the signal, then rotate the gradient to a different direction. Acquire the signal again. Do this for several polar and azimuthal angles of the gradient direction, keeping the amplitude fixed. Okay, and then you do an inverse radon transform to do the projection reconstruction. So you're measuring projections of the object, 1D profiles of the object, and then you do a reconstruction. This is much like X-ray CAT scans. So the initial MRI experiments followed that particular philosophy of projection reconstruction or algebraic reconstruction using inverse radon transforms based on projections that are measured. However, in the case of MRI, these projections are measured by using constant gradients in fixed orientations. And only after finishing the data acquisition, you turn the gradient to a different direction, keeping the amplitude fixed. But soon it was realized that you can do it in a smarter way, and that goes by the name of Fourier imaging. And finally, you have echoplanar imaging, which is a single pass raster through 2 or 3 dimensional in reciprocal space or K space. In MRI also, we talk about a reciprocal space or a K space. Although it is physically not a diffraction experiment, you can still use the mathematical language which you use for diffractometry. And one of the things we use for diffractometry descriptors is a reciprocal space or the K space or the inverse space, right? And that is the single pass raster in K space or reciprocal space. In one single scan, you can go through all of the 2-dimensional or 3-dimensional space within the range of interest and produce the image. And that makes it a fast technique, and that is what echoplanar imaging is. So the first 2 Nobel Prizes for MRI were won by Lauterbur for his invention of projection reconstruction MRI, and by Mansfield, who eventually developed echoplanar imaging for MRI. And the protocols involve a spin echo or a multiple spin echo using a train of radio frequency pulses, or a gradient echo, or a multiple gradient echo. Now, in the time available, how much time can I take? Can I take another 30 minutes? Can I take another 40 minutes?
Yes, sir.
40 minutes?
Yes, sir.
40 minutes is okay?
Okay, sir.
Yes, sir.
Okay. So how does MRI work? Once again, summarizing it. It is not a scattering or a diffraction technique. It is a resonance technique that employs resonant electromagnetic radiation to reorient nuclear ensemble magnetization and the individual nuclear magnetic moments. The nuclear ensemble magnetization at equilibrium is oriented in the direction of the external Zeeman magnetic field or the polarizing magnetic field, and you can bring it into a direction in the transverse plane for the ensemble magnetization by using the resonance technique, okay, which is resonant electromagnetic radiation. By resonance, we mean that the frequency of electromagnetic radiation is closely matched to the precession frequency, okay, and the image resolution is unrelated primarily to the wavelength of radiation. Any system of diamagnetic molecules can be imaged. Now, a lot of medical doctors keep asking me, does this mean that water has become magnetized or water is magnetic? Please let us be very, very clear. We are measuring the MRI of the water proton nuclear magnetic moments in our body, but our body has not been magnetized. The water in our bodies has not been magnetized, except for the iron in the hemoglobin of our blood, okay, which becomes paramagnetic when the oxygen has been stripped away from this hemoglobin. When oxygen is bound to the hemoglobin, that's diamagnetic. But when oxygen has been stripped away from the blood to provide the energy, let us say, for the body processes, for the physiological processes, then you get deoxyhemoglobin, and that is paramagnetic. But that doesn't make the body paramagnetic, and except for this deoxyhemoglobin, nothing in our body is magnetic or even weakly paramagnetic. It is all diamagnetic stuff. And please remember that the diamagnetism due to the electrons, let us say in the water molecule, is much, much stronger than the paramagnetism due to the nuclear magnetic moments of the proton nuclei in water. So my medical friends have a lot of difficulty in visualizing or comprehending this concept. They keep thinking that water has somehow become magnetic. No, gentlemen and ladies, it has not. Water is its usual self. It is a diamagnetic molecule. The weak nuclear paramagnetism that we are talking about is much orders of magnitude weaker than the electronic diamagnetism of the water molecule. So water remains diamagnetic. Nobody has magnetized it. But what are we talking about? How are we measuring this very weak nuclear paramagnetism in the presence of a much stronger electron diamagnetism of the water molecule? That is because the precession frequency of the electrons depends on the electron gamma. The precession frequency of the electron magnetic moments is also going to be given as omega naught equals minus gamma b naught in the absence of gradients. The B naught is common to all the species in the body because the body is lying in a magnetic field of intensity B naught. B naught is common for that body. But the gamma is different for proton nuclei as compared to electrons. And the gamma for electrons is minus 658 times the gamma for electrons. So please remember, it is the magnetic moment of the proton which confers on it a unique precession frequency. Diamagnetism, there is no net precession because this is not paramagnetism of electrons we are talking about, it is diamagnetism. But the point is that any precessional motion on the surface of the cone that we visualized is at a totally different frequency at a given field when you compare protons with electrons. And so we are saying that, yes, this is a very weak nuclear magnetism. It is swamped and dominated by the electron diamagnetism of the water molecule. But yet, we can selectively pick out this needle in the haystack. Much weaker nuclear paramagnetism in the presence of the much stronger electron diamagnetism. How are we able to do it? Because of a unique precession frequency of the proton magnetic moment. And that is what the resonance process allows us to do. Ladies and gentlemen, you may be familiar with the fact that people use a Faraday balance or a Guy balance to directly measure magnetic susceptibilities of paramagnetic molecules, where you have unpaired electron magnetic moments. Like oxygen is paramagnetic, nitric oxide is paramagnetic. Any amount, any number of free radicals are paramagnetic. Okay, and similarly transition metal complexes, rare earth complexes are paramagnetic, and therefore they have a paramagnetic Curie susceptibility when there is no cooperativity. And you can measure this by putting the sample in a magnetic field, which, like in the original molecular beam experiments of Stern and Rabai, it has a huge magnetic field gradient, and there is a force due to the gradient on the sample. So when you weigh the sample in the presence and absence of this magnetic force, which comes from an inhomogeneous magnetic field, so you take a chemical balance. From one pan of the balance, you hang your sample in a tube between the poles of a magnet. This magnet is highly inhomogeneous, so when you turn it on, it generates a magnetic force. And of course, you remember that taking the mass is really taking the weight. Okay, so there is a force due to the acceleration due to gravity, and the mass times the acceleration due to gravity is what we are measuring as the weight. And now you're changing that force by turning on the inhomogeneous magnetic field. There's a built-in gradient in that magnetic field, which you use for the Stern experiment or the Rabai experiment with molecular beams. They're not homogeneous magnetic fields. And similarly for the susceptibility measurements, Curie susceptibility measurements, you will use something called the Guy balance or the Faraday balance or a vibrating sample magnetometer. And these also involve inhomogeneous magnetic fields, and that exerts a magnetic force which changes the apparent weight of the sample. And then you can measure the magnetic susceptibility. But nuclear paramagnetic susceptibilities are so weak under normal conditions that you cannot measure the nuclear paramagnetic susceptibility by such a method. By the Guy balance or a Faraday balance or a vibrating sample magnetometer method, you cannot measure the nuclear paramagnetic susceptibility, which is far too weak, even as compared to electron diamagnetic susceptibility, leave alone electron paramagnetic susceptibility or ferromagnetism and so on. So here you need to use resonance. And the resonance frequency of the proton nuclear magnetic moment is totally different as compared to any possible precession of an electron spin. If you have unpaired electrons, okay, like in oxygen or nitric oxide or some inorganic complexes or free radicals, you have unpaired electrons. They have magnetic moments, they will precess in the magnetic field, but the precession frequency is totally different because the magnetogyric ratio of the electron is minus 658 times the magnetogyric ratio of the proton nucleus. And so we are able to pick the needle from the haystack. So please remember, we use MRI typically just with water molecules, and water is not magnetic, it is diamagnetic. And still, please understand this and explain it in case your students are worried about this. Because I find a lot of very experienced medical doctors are completely puzzled by this, and they misunderstand the situation, saying that somehow we magnetize the water. We have not. The water is still diamagnetic. But what we are doing is we have amplified the paramagnetic susceptibility by the resonance procedure. And all it means is that while the diamagnetic susceptibility is static, we have made the paramagnetic susceptibility, which is much weaker. However, we made it precise. And when it precesses, this magnetic moment cuts a coil. And you know, when a magnetic moment cuts a coil, you have a Faraday induction. That is the electromotive force. So this is just called a nuclear induction experiment. It's like the dynamo. When we were riding bicycles as kids, you know, we would have a dynamo. So on our bicycle, typically we put this can at the back wheel, which has a rotating disc when it is in contact with the tire. And then below that is a can, which has a coil suspended in a fixed magnet. And then when the wheel rotates, the disc rotates with it on this top of this can. And that means the coil which is connected to the shaft of this disc rotates in the fixed magnetic field in the cam. And then an EMF is generated, and that is fed by wires to the headlight on the bicycle. That's what we are doing. Our detection of magnetic resonance is just like the dynamo. It's called nuclear induction. And all we are saying is this induction occurs at a characteristic frequency, which enables us to measure it, although it is very weak. The voltage which you will get from the NMR resonator is typically going to be of the order of microvolts, and if you get very lucky, millivolts. That means you are competing against noise voltage. So the signal to noise ratio is a huge problem in nuclear magnetic resonance imaging and so on. So you got to do special things to do MRI to improve the sensitivity of detection or the signal to noise ratio of the EMF that you detect by this nuclear induction process or this dynamo effect. Okay, so you get the magnetization of the entire assembly of water molecules or the ensemble of proton magnetic moments of the water molecules in the head or whatever portion of the body you're imaging. You get this ensemble magnetization and rotated by a resonant radio frequency radiation pulse to a direction orthogonal, let us say, to the Zeeman magnetic field B naught, which is static. And then you get an induced EMF. And that is what we measured. So you have the Z magnetization, where Z is the direction of the magnetic field. You cannot measure it. It's too weak. Because nuclear paramagnetism, as I kept saying, is much weaker than electron diamagnetism. You produce a non-equilibrium state of the nuclear magnetization. That means you tip it into a direction, okay, which makes an angle with respect to Z. And the best results are obtained if the magnetization is tipped to make a 90-degree angle with respect to the Z direction, which is the direction of the B naught magnetic field or the Zeeman magnetic field. Then you get the maximum induced voltage. So you may call that as the XY magnetization. And then you detect it. So the time dependence of the ensemble magnetization is given in this equation. There is a precession which is described in the first term on the right-hand side of this equation. And the second, third, and the fourth terms tell you about the relaxation. Why are we worrying about relaxation? We just now said that to produce a signal, we have to produce a non-equilibrium state of the magnetization of the ensemble of spins. But if you produce a thermodynamic state, which is a non-equilibrium state, the system of nuclear magnetic moments will also try to go back to their thermodynamic equilibrium state. And this process by which the thermodynamic equilibrium is restored without using electromagnetic radiation. You use electromagnetic radiation to produce a non-equilibrium state. Then there will be a spontaneous return to equilibrium. And this return to equilibrium can be for the Z component of the magnetization of the nuclear spins, and it can be for the XY component. And the Z direction is unique. It's a direction of the Zeeman field, and that has a certain time constant associated with its relaxation. That is the T1 time constant. And in the XY plane, you have another characteristic relaxation time, that is the T2, or the transverse relaxation time, T2. The longitudinal relaxation time is T1. And this can produce a contrast in the images. So the mobility of the water molecules will govern the value of the time constant T1, will govern the value of the time constant T2. And therefore, the mobility of the water molecules can, because they influence T1 and T2, the mobility influences T1 and T2, this will influence the contrast in the MRI image. These are simple phenomenological first order kinetic equations which describe the time rate of change of the Z or the X or the Y component of magnetization. We'll not worry about the details here, but please focus your attention on the time constants T1 along the Z direction, which is the direction of the B naught Zeeman static magnetic field, and you have to have the other time constant which is unique in the XY plane, no matter in which direction of the XY plane. This will govern the X component's relaxation to equilibrium and the Y component's relaxation to equilibrium, both by the same time constant T2. Please remember the radio frequency which is used has to be along this XY plane also. Otherwise, the non-equilibrium state cannot be generated unless the radio frequency is polarized with a component perpendicular to the z direction. You cannot produce a non-equilibrium state. So after the excitation by a burst of radiation, the magnetization, which is starting from the z direction as shown in this column vector, the third component in this column vector is m naught, which is the equilibrium magnetization along the z direction. And this is rotated by the pulse. Okay, in this case I have used a pulse along the minus x direction of a special coordinate system called rotating frame, and that's a 90-degree pulse along the minus x-axis, so it is like a 270-degree pulse along the plus x-axis. And then I use the rotation matrix in this rotating frame. The x-axis is the axis of rotation, and the cos theta and minus sine theta are the sine theta and the cos theta. The cos thetas are the diagonal elements, and the plus or minus sine thetas are the off diagonal elements of this rotation matrix. And the result is you have produced a component of the magnetization now which is fully along the plus y direction. By using a 90-degree rotation along the minus x direction of this rotating frame, which is a frame which corresponds to the rate and sense of precession of the nuclear magnetic moments. So imagine you are sitting on a coordinate frame which is moving in the same direction and at the same rate as the nuclear magnetic moment precession. Okay, remember the cone of precession we talked about in the initial slides. That's the same thing. So if you're observing everything sitting in such a frame which is moving in the same direction and at the same rate as the precession of the nuclear magnetic moments, that's your rotating frame. Okay, so in such a frame, if you give a 90-degree pulse along the minus x-axis, that is equivalent to a 270-degree pulse along the plus x-axis. This is the rotation matrix. You apply it to the magnetization column vector, and this is what you then see. Okay, the z component of this column vector is rotated into the plus y direction. So you are visualizing it this way: magnetization along z is rotated to the plus y direction. It is then starts dephasing because you've created a non-equilibrium state, and it produces a decaying induction voltage. This is called the FID, or the free induction decay, and then finally it is going to be completely randomized. And the way that this decay takes place is governed by this equation, that dmy by dt, because you're starting about the y component, which is non-zero soon after the 90-degree pulse. And this then will give you this kind of a decay governed by this relaxation equation, which you can integrate, and you see that the time variation of the y component of the ensemble magnetization is given thus. Okay, and you talk about spin packets or spin isochromats. So the splitting up of the total magnetization of the nuclear magnetization of the water protons gradually gets split up into small bunches. These bunches are called spin packets. Okay, these are spin magnetic moments, each with its own characteristic, slightly different precession frequency. So you call them as different spin packets or different spin isochromats. Okay, that's what you do. Now you can picture this precession by such a rotation matrix. You can picture it by such a vector diagram, because magnetization is like a vector in three-dimensional space. You can use a three-dimensional rotation matrix to see what is happening. You can give the corresponding vector pictures. You can do all that. You can also do it by other methods. We will not worry about it. But then the important thing is you don't want the signal to decay so fast. So imagine that you gave a 90-degree pulse this time from thermal equilibrium, rotated the ensemble magnetization to the minus y direction by a 90-degree pulse along the plus x-axis of the rotating frame. Then it is going to split into several spin packets or spin isochromats. The induced voltage is going to start decaying, but now you turn around the system of spin packets or magnetization isochromats by a second pulse, which is a resonant burst of radiation that will rotate the magnetization by 180 degrees instead of by 90 degrees. You see here, you rotated this with a 90-degree pulse, which means the magnetization went from Z to Y if the pulse was along the minus X direction, or 270 along plus X. Just the magnetization is rotated by that angle. You call it the 90-degree pulse if the magnetization is rotated by 90 degrees. You call it a 180-degree pulse if the magnetization is rotated by 180 degrees. That's what you do now. The dosai திருப்பி போடுற மாதிரி, this bunch of spin isochromats is like flipping the pancake by a 180-degree pulse, and it comes here, and then you see what has dephased due to magnetic field inhomogeneities, not due to irreversible relaxation, but due to reversible dephasing by magnetic field inhomogeneities. That can be rephased, and you get a so-called echo. You started with magnetization along Z. Look at this first column vector in the first row. When you see, you have taken this after the first 90-degree pulse along the plus X direction, you have produced a minus magnetization along the Y direction. The entire ensemble magnetization M0 initially along Z by 90-degree X pulse in the rotating frame goes to the minus Y direction. Minus sign here, and then the M0 for the Y component. And then you give the 180-degree pulse and give some more time. Equal time tau before and after the 180-degree refocusing pulse. Then you produce an echo, because you see the magnetization is back along the Y direction. Instead of minus Y soon after the 90, it comes to plus Y, a tau period after the 180. So the echo is formed in this manner. So you see that you are rephasing the dephased magnetization. And this is how you can picture that voltage. You had a free induction decay soon after the 90-degree pulse. Soon after the 180-degree pulse, it will start rephasing in the build-up part of this exponential. Then it reaches the maximum, like in that previous slide, and then it starts decaying again. Then this is what is called the echo. Okay, we'll not worry about other formal ways of describing this process, but then you can do the Fourier transform of this time-dependent signal, the free induction decay or the echo. And you see that the free induction decay, when you do a complex FT, you'll get a real part, which is a so-called Lorentzian absorption shape, and you get an imaginary part, which is a so-called Lorentzian dispersion shape. And the amplitude of Lorentzian absorption is just when omega is 0, that means right on resonance. Omega is the frequency offset from resonance. A is like 1 over T2 star. We have introduced T2 star earlier, right? In this slide here, we introduced T2 star. Okay, that is the apparent transverse relaxation time. Instead of T2, we are calling it T2 star. T2 is the time constant of the genuinely irreversible transverse spin relaxation, but some part of it could be reversible due to magnetic field inhomogeneities, other instrument imperfections, and that then governs the decay of the transverse magnetization at a faster rate by a time constant, which we call as T2 star. Okay, that's the apparent T2. And that is what we are saying here, that A, little a in this equation is like 1 over T2 or 1 over T2 star. Omega is the frequency offset from the correct resonance frequency. So you see the maximum of the absorptive part of the FID's complex FT is going to have the amplitude 1 over A, because you put omega is equal to 0, you get the amplitude 1 over A. But suppose you have an echo. An echo had a build-up part, reaches the maximum, and then it fell off again in a decay. That's like a back-to-back pair of FIDs. And then you see when you do the Fourier transform, the same complex FT with e to the power minus I omega t as the basis function. You see now the real part is twice the amplitude that you got with the FID now when you're dealing with the echo. And the imaginary part is 0. It's easy to understand why you get twice the amplitude of the real part, because after all, this echo is like a pair of FIDs back to back. So you'll get twice the amplitude of the FT of the FID when you take the FT of the echo. But the nice thing is the imaginary part vanishes. So in MRI, we will always deal with echoes for a number of reasons. That is because echo has an extremely useful characteristic. Look at this thing again. Soon after the 90-degree pulse, the FID started. But in the electronics, the receiver cannot pick up the induction voltage soon after the pulse because the receiver has to be shut down during the high power transmitter pulse. The transmitter pulse may have a wattage of about a kilowatt in MRI. And the signal, as I said, the signal voltage is typically between micro to millivolts. So there's no way you can detect a micro or a millivolt when you are getting a transmitter at the same frequency with a kilowatt of power. So you have to shut down or blank out the receiver during the radio frequency pulse and then unblank the receiver at the end of the pulse. But then you cannot instantaneously, the receiver will not get unblanked and arrive at its equilibrium state. It will be saturated for some time after the high power pulse. And therefore, you can start detecting the FID only after a certain delay in which you are losing part of the initial signal. Okay, the FID, the free induction decay signal, the initial part will be lost because the receiver is dead during that time. You have unblanked the receiver soon after the transmitter RF pulse, but the receiver is trying to recover itself, and this is a receiver recovery time which could be of the order of, let's say, 5 to 20 microseconds or even longer, depending on the resonator that you're using. Okay, the ring down time of the resonator and the Q factor of the resonator. So you see, when you have an echo, the receiver can be dead. You don't care because the echo is slowly starting to build up. So even if this is the initial portion of the echo, it is completely dead receiver, doesn't matter. There's no signal. By the time you start getting signal, the receiver has recovered. So you see that the receiver dead time is not going to end up in you losing any signal if you are picking up the echo, not an FID. That's one of the main reasons we use an echo. It's also true when you want to switch gradients. You want to give time for the gradient and the eddy currents due to gradient switching to settle. And the echo is like a delayed pair of FIDs, a delayed pair of back-to-back FIDs. And this delay allows the receiver to settle down after being blanked and unblanked. It allows the gradients to settle down after being switched, and the eddy currents to die down also after switching. Okay, so these are two important advantages of using echoes, and it gives twice the sensitivity as compared to an FID. Now here I've talked about some power calculations. That's not important for you people. You must be expert at this. Okay, the decibel is what we use as a measure of power. 10 log to the base 10 of P2 by P1, or 20 log to the base 10 of V2 by V1. But in terms of peak to peak voltage of a sinusoidal excitation signal or received induction signal, which are all sinusoidal, okay, sine wave or a cosine wave, then you convert from the peak to peak voltage to the RMS voltage. Okay, and then you use the factor from peak to peak voltage to RMS voltage conversion, multiply the peak to peak voltage by the factor 1 over 2 root 2. And then to convert this to power into a 50 ohm load, end up essentially taking this, uh, you know, square of the peak to peak voltage and divided by 400. That gives you the RF power into a 50 ohm impedance. This takes care of 1 over 2 root 2 whole squared, V squared by R or Z, right? So V squared is going to be the RMS or the mean squared power, and that is 1 over 8 times the peak to peak power. And then into a 50 ohm load, so V squared by Z, that is the peak to peak voltage squared divided by 400. Okay, so that's the usual thing. And the advantages are put down here again. You get rid of the receiver dead time, you get rid of the gradient settling time problems, and so on. And this is how you provide an one-dimensional profile in the Fourier imaging mode. You have a sample of water, which is this tube here. It is in a solenoidal magnet in this case, which is the outer coil, which is in a Helmholtz configuration. Then you have the red coil, which is for transmitting and receiving the RF pulses. And in between the outer Helmholtz coil and the inner red RF coil, you have the anti-Helmholtz coil for producing the gradients. And with the gradient current switched off, you'll get an FID which looks like that from the water protons in the tube here. And you get a single sharp line, which may have a width of only 1 to 10 hertz. But lo and behold, if you turn on the gradient current in that inner black coil, okay, the anti-Helmholtz pair of coils. Okay, then the red one is the RF coil. The outer black is the Zeeman field Helmholtz coil. The inner black is the anti-Helmholtz gradient coil. Now, when you turn on the current there, your FID, it changes shape from a simple beat to a beat, I'm sorry, a simple damped oscillation. It changes from a simple damped oscillation or FID to an oscillation which is damped and which has beat notes. And then you see this sharp Lorentzian shape of the Fourier transformed signal is going to give this shape now, which is a top hat function, which corresponds to the profile along the Z direction, because this gradient was along the Z direction. See, the anti-Helmholtz coil has its axis along Z, which is the axis of the magnetic field. And therefore, the shape of the tube along Z for the cylindrical tube, this is the profile that you get. Walked across a little too far. Where was this? Yeah, that's the profile. So you got your one-dimensional profile. Now you can use this gradient, turn its angle, but you got to have 3 pairs of gradient coils along X, along Y, and along Z in the static coordinate system. This is not the rotating coordinate system of the nuclear magnetic moment precession. This is a static laboratory fixed coordinate system where Z is along the Zeeman field. That is common to both the static frame and the rotating frame. And then X and Y, they're both transfers to Z. But in the rotating frame, the X and Y coordinates are moving at the same rate and at the same sense as the nuclear precession. Whereas in the static laboratory frame, they are fixed, the X and Y. Okay? So that's what you do in the projection reconstruction method. You get a series of projections because now the resonance frequency is given by this frequency dependence. Nu is equal to minus gamma by 2 pi times the Z coordinate times the gradient along Z. And so instead of taking the Fourier transform and representing it along the x-axis as a frequency axis, you can now say that gamma is a constant, the gradient is supposed to be constant, 2 pi is a constant, and therefore the variable frequency along the horizontal axis is actually the variable Z coordinate. This is how the frequency of the signal encodes for the spatial coordinate. Okay, so you can take this signal and you can say, yes, when I take the FID, which is a function of time, when I do the Fourier transform, I get the signal amplitude as a function of frequency. But because the frequency is proportional to Z, I can change this axis and call it as a labeled with the Z coordinate instead. Okay, like here. That is how you get the one-dimensional profile, and the magnetization then rotates in this direction. So you can write the rotating magnetization vector in this particular form. Okay, and you can define your reciprocal space vector as k in the read gradient direction, because you're reading out the signal now, and this is defined k subscript r. The reciprocal space axis along the read gradient direction is defined as minus p is equal to +1 for us. Okay, take it as +1. Don't worry about this p. Assume that p is -1. Actually, minus p is +1. P is -1 for us by default. So minus p is +1. So you have e to the minus this thing. Gamma, the little r coordinate along the read direction times the gradient along the read direction times t. That's how you define your reciprocal space vector. And you can then formally talk about the projection of the distribution function rho. Okay, which is what you're trying to image. You're trying to image the density distribution function or the mobility distribution function rho, which is the function of x, y, and z coordinates in the fixed laboratory frame. So I'm using these coordinates with the capital letters x, y, z. In the rotating frame, I will use small letters, little x, little y, little z. But the gradients are fixed coils and they are static laboratory coordinate frame. So the density function of the proton density or the water mobility is expressed in the static laboratory frame. And in the projection reconstruction method, when we take a projection along the Z direction, this is like saying that we have integrated the density distribution function over the X and Y coordinates to get this profile along Z. And this profile along Z, okay, is going to give you a signal through this Fourier transform. You see, what we are saying is a signal which, as we said, has this particular phase factor. This is what we said. Okay, and this is a signal we measure. So what we measure is actually the density distribution function, which gives you the magnetization m naught as a function of z coordinate, times this phase factor, or the k-space component, reciprocal space component. This is a phase factor when the magnetization rotates in the xy plane, and we are recasting this in the reciprocal space language. Okay, and you see the signal we get is just actually the Fourier transform of the density distribution function. So what do you do to get the density distribution function? You take the inverse Fourier transform of the measured signal. That's it. So this is how you reconstruct the image in MRI. Because the measured signal is the Fourier transform of the density distribution function, you can then reconstruct the actual density distribution function by taking the inverse Fourier transform of the measured signal, which is a function of the reciprocal space. And when you do the Fourier transform, okay, then you get the image as a function of the spatial coordinate. Okay, that is the trick. So a simple Fourier transform will allow you to get the image reconstructed. There is a resolution limitation, which is governed by the line width of the NMR signal in the absence of the read gradient. And that is, you cannot do better than this. But we've already seen other limitations like diffusion and the gradient amplitude and the sensitivity per voxel or pixel. All of this will determine the limit on the resolution you can get. You seldom can go better than 10 micron resolution. But the field of view in the read direction is the next thing you want to worry about. And that can be defined like this. It is the band over which the spectrum of signals is obtained in the presence of a gradient divided by the read gradient amplitude, expressing the numerator and denominator in compatible units. Okay, the band over which the signals are acquired in the presence of read gradient divided by the read gradient amplitude expressed in compatible units. This gives you the field of view in the read direction. So if you want to have smaller and smaller field of view, you must have a larger and larger gradient. Okay, so you scan the image simply by taking the FID readout as a function of time, and since our reciprocal space vector along the read direction kz was simply p is equal to -1, and this was simply gamma gz t. And gamma and gz are constant. T is the variable during which you acquire the signal. Therefore, you can say kz in this case is simply proportional to t. So as the time runs during data acquisition, your kz vector is being scanned. The reciprocal space vector is scanned. Okay, that's what you're doing. The field of view is defined thus, and the scan is just the passing of time during the acquisition time of the signal. Okay, so this is the imaging with constant gradients, reconstruction, and in k-space, this looks like a radial scan in k-space. But that's not how we do it nowadays, because there are several issues. The radial scan procedure or the projection reconstruction procedure is the same principle as X-ray CAT scans, except you use gradients and RF pulses here, which you don't do in X-ray CAT scans. Issue is that uniform data sampling is not there. You see, you're digitizing these data. Obviously, the density of points closer to the origin of k-space is much higher than the density of points in a small, area, infinitesimal area. As you go farther and farther out in k-space, the density of points is smaller and smaller. So you have non-uniform sampling in k-space when you do the radial scan procedure, which is what you do in the constant gradient readout of the signal. And this is not good because it gives rise to, and after each pass, you rotate the gradient, keeping the amplitude fixed, changing the orientation, the polar angle of the gradient, the azimuthal angle of the gradient in three-dimensional space, and get another scan and repeat it for various values to the polar and azimuthal angles. That's how you build up the entire data set, and you do an inverse radon transform, you get the projection reconstruction. But obviously, there's non-uniform sampling in k-space, in reciprocal space. So you get image artifacts. So you got to do some algebraic reconstruction, smoothing the data set suitably by interpolation. So you have to do that, okay? Now you have various other problems. So you don't prefer that. And what we do this nowadays is a Fourier imaging or an echoplanar imaging. If you can switch the gradients fast, you can do the Fourier imaging or echoplanar imaging. What is fast? You cannot typically switch faster than 1 millisecond for a gradient in a whole body MRI scanner. Is the T2 star or the T2 much shorter or of the order of or much longer than the gradient switching time? If the T2 star or the T2 of your nuclear ensemble magnetization is much shorter than the gradient switching time, so the transverse magnetization will disappear by the time you switch your gradient. You cannot measure a signal anymore. There's no induced EMF. So you cannot do a gradient switching and do a Fourier imaging or an echoplanar imaging unless your T2 or T2 star is long enough as compared to the gradient switching time. Fortunately, in soft matter, this condition is not difficult to satisfy. You often have T2 or T2 star that are inherently longer than the gradient switching time, and therefore we are able to pulse the gradient, switch them back and forth, and don't just have a constant gradient and take a scan of the signal and then change the gradient orientation. Instead of that, in the process of the scan itself, you can pulse and switch the gradient. Okay, but then you need to worry about various other issues like the excitation RF pulse profile. So if you have a rectangular RF pulse profile, the excitation profile is to zeroth order by Fourier transformation of a top hat function, you get a sinc function. And if you have a sinc function, is the time domain envelope shape of the RF excitation pulse, you get a top hat function in the Fourier transform. And this is the Fourier transform of the time domain excitation pulse envelope is like the zeroth order spin response from the ensemble magnetization, but it's only a zeroth order response. Okay, so you have to worry about, now you see, when you have this kind of an excitation response, excitation is top hat profile in time domain, the response function to zeroth order in frequency domain is an oscillating function. It's a sampling function or the sinc function. This is not constant. In time domain, it is a gate function or a top hat function. I'm sorry, there's a small distortion in this image. It should be really flat on the top. So the pulse is zero everywhere, and then the pulse is switched on to reach its maximum amplitude. It contains all these RF oscillations during the top of the top hat, and then the pulse is switched off. So please remember, this is just envelope of the pulse, which we are showing as a top hat. But the pulse is switched off, then it is switched on. With a constant amplitude, the oscillations of the RF will take place. Then the RF is switched off, and there is zero amplitude. And then the envelope of the RF in time domain is going to have this envelope in the corresponding frequency domain. And this is a reasonable zeroth order approximation to the spin magnetization response. The response function in frequency domain will have this. That's not nice. It's varying as a function of frequency. And frequency stands for spatial coordinate in the image. That means different regions of the image will have different signal intensities. You don't want that. You would like to have a constant intensity as a function of coordinate, except for inherent variations in the proton density or the water mobility. It should not be just from the response function, but from the excitation profile, but instead it should be from the actual PD contrast or from the mobility contrast. Therefore, you will choose funny shapes, maybe a sinc shape of the envelope in time domain, or very many other shapes, a hyperbolic secant shape, a Gaussian shape, a Hermite polynomial shape, and so on. These are often, you will not use the default rectangular pulse or block pulse shape for the envelope of the RF pulse in time domain. Instead, you will use a suitably synthesized envelope shape of the excitation pulse in time domain, which gives you a desirable characteristic to zeroth order in the spin response function, which ideally should look like a gate function or the transfer function. So it is a constant response from the chosen slice, except as modulated by the proton density or by the water mobility or by the diffusion, right? And everywhere outside the chosen slab, it should have zero response. That's what you would like. So you use variety of pulse shapes to do this. We don't have time to go into the details. I just want to give you a few more points and we'll stop. Can I take another 5 minutes?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
We started late, but now I'm exceeding my time. That is why I'm seeking your permission. 5 minutes, okay?
No, sir. No problem, sir.
Yeah. We can produce echoes by two different ways. The so-called gradient echo and the so-called spin echo. We don't have to talk about this in detail now. We don't have the time. It's all there in my PowerPoint file, but then we cannot go through it in detail now. It starts from the echo that we talked about earlier. We gave a 180-degree pulse to produce the echo. You remember from the FID, after the 90-degree pulse, we gave a delay, tau. Then we gave a 180-degree pulse, then an equal delay, tau. And when we acquired the signal, now it looks like at the equal delay, tau, at that point of time, you get a maximum signal, which is the top of the echo. And if you start receiving the signal or acquiring the signal soon after the dead time following the 180-degree pulse, you can see the back-to-back pair of FIDs more or less. And this kind of echo, which is produced by a resonant 180-degree RF pulse, is called the spin echo. But you can also produce an echo by dephasing the magnetization using the gradient, because the gradient generates a frequency dispersal and therefore a phase dispersal. So if you reverse the gradient, it will produce the reverse phase dispersal. So if you give a phase dispersal by a gradient of a fixed amplitude working for a fixed time, you can reverse that phase dispersal by giving an opposite gradient amplitude for an equal time, or double the opposite gradient amplitude for half the time, right? That's a gradient echo. Let's just put it like that, okay? And please remember that the phase is just given by this minus p gamma times integral over r dot g dt prime. The phase at time t is the integral over g dt prime, dt primes integrated over 0 to t. We are assuming that the molecules are not moving, so they have a constant position vector which are independent of time. Right at the end, we'll make a point about how to take into account the movement, the motion of molecules, use that to measure the velocity of flow, which is very important in MR angiography, or the acceleration in flow, like in turbulence. All of this can be measured by MRA, ladies and gentlemen, without using a catheterization or other painful invasive procedures, without any exogenous contrast agent. Just the flow of blood can be measured by magnetic resonance imaging by a special technique known as magnetic resonance angiography, where you will use special gradient pulse reversals to encode for discriminating static spins as compared to flowing spins. Flowing spins with constant velocity and static spins can be discriminated against spins that are flowing with a constant acceleration, and so on. Okay? Because you can expand this position vector r of a spin as a Taylor series in the position coordinate, and by using a suitable waveform of the gradient, whose zeroth moment, first moment, and second moment with respect to time have desired values, you can then map desired velocity flow or acceleration or only static spins selectively. That's what we use for angiography. Okay? So you can produce gradient echoes, or you can produce spin echoes with a 180-degree pulse. The gradient echo is produced without a 180-degree pulse, just by having a gradient and then reversing it. Okay? And when you now say that you have a gradient, in the presence of the gradient, you have a problem of the bandwidth. You see, we talked about the bandwidth of the pulse here when you looked at the excitation pulse. What is the frequency range over which the spin ensemble is excited and the magnetization is made transfers to Z? That is a finite range. You cannot put a gradient, spread the resonance frequency over hundreds of kilohertz, and then hope to uniformly excite the spins over hundreds of kilohertz or a megahertz. So this is one of the problems in using a constant read gradient. You cannot bring the transverse magnetization into the, you cannot produce the spin magnetization into the transverse plane with uniform amplitude when you have a gradient on. And therefore you say, no, let me pulse the gradient on and off. Provided my pulsing time is much shorter than my T2 or T2 star, I can do this. And then I need to excite only a slab or a slice of spins. Therefore, a limited bandwidth of the RF excitation will do. So it's a necessity because my RF efficiency is poor. But I make a virtue of necessity by selecting a slab by using a slice selection gradient. And the slice thickness is given by this formula. It is the radio frequency pulse bandwidth which you're using for excitation divided by the gradient in whose presence you are giving this excitation radio frequency pulse. Again, you must express the RF pulse bandwidth and the slice gradient in compatible units. You get the slice thickness. So the Fourier imaging or the echoplanar imaging, even the projection reconstruction imaging, if it is 2D or 1D, would like to use, if possible, if you can switch the gradients. For Fourier and echoplanar imaging, you have to switch the gradients. For projection reconstruction, you don't have to. But then if you are able to, then you can pick up slices. So you use a slice gradient, then switch off the slice gradient. Let us say you use a slice gradient in the slice direction. You may call this as the Z direction. Then you will excite a slab or a slice of spins only from a plane parallel to XY. If your gradient for picking the slice is along Z, you pick the spins and bring them into the transverse plane by a 90-degree pulse. All spins in the XY plane or a plane parallel to XY are brought into the transverse plane by a 90-degree pulse in the presence of a slice gradient along Z. And the thickness of the slice is given by this formula. And then having brought it into the transverse plane by uniform excitation pulse, we can then worry about what shapes. I'm not going into the details here. We have to worry about the non-idealities of a slice selective radio frequency pulse. So you're using an RF pulse shape envelope, which may be Gaussian, it may be Hermite, it may be hyperbolic secant, it may be a sampling function or a sync function. We just indicate this synoptically like this, some funny shape which is not a top hat shape, but then it will produce non-idealities in the phase distribution of the transverse magnetization. So you have to generate a gradient echo. The slice gradient is reversed, and at the end of the slice reversed gradient, you will get transverse magnetization, which is all refocused in one direction in the transverse plane. If you looked at the transverse magnetization produced soon after the pulse, after the positive lobe of the gradient and after the RF pulse, the transverse magnetization produced is going to be fanned out in the XY plane. It is dephased in the XY plane. We showed the pictures of dephasing earlier. Now what we are saying is we don't even have to wait some time tau, just a shaped soft selective pulse. During this pulse, which is of the order of 1 millisecond, you will have automatic dephasing of the transverse magnetization that is produced. That's going to destroy your signal. So you rephase the signal into a fixed direction in the transverse plane by reversing the gradient, producing a gradient echo. So that is the slice selective gradient. And then you use this kind of a density distribution function at some coordinate with a finite thickness of the slab at the point RS naught with a small delta R as the thickness along the slice direction. You then want to map the density distribution function or the mobility distribution function as a function of the phase gradient and as a function of the read gradient. Now you must ensure that the slice gradient, the phase gradient, and the read gradient are all orthogonal to each other, so that all the three dimensions of orthogonal three-dimensional Cartesian space are covered. So the slice gradient, if it were along Z, let's say, then the phase gradient encoding the phase of the magnetization in the transverse plane must be, let's say, along Y, and then the read gradient encoding the frequency encoding of the transverse magnetization must be along X. So Z direction of the slice gradient, let's say, Y direction of the phase encode gradient, let's say, and then the X gradient of the frequency encode gradient. And then for a fixed amplitude of the phase encode gradient, GP naught, this is the signal you get. It is as a fixed value of minus P gamma GP naught. And remember that this minus P GP naught times TP was the KP when you multiply it by TP, right? So we can put all of this together and we call this minus P gamma GP naught TP as KP naught. So this whole thing is multiplying RP. So you have this thing coming out as e to the power I KP naught RP. That's a fixed value of the phase encode gradient amplitude. Then you have the frequency encode gradient, which is also fixed, but we are acquiring the signal as a function of the free induction decay time or the echo time, build up and decay of the echo. And therefore TR is a real variable, and therefore KR is a real reciprocal space variable. But KP is found pointwise for each amplitude of the phase encode gradient. So the function we have got in reciprocal space is S, little s, at Kp naught as a function of Kr. And this is the three-dimensional density or mobility distribution function mapped parametrically for one particular value of the phase encode direction, Kp naught, for all values of the Kr. In order to make this also as a continuous variable or a discretized variable, you got to repeat this experiment for different values of the phase encode gradient amplitude. So then if you do that, you will get the signal acquired as a function of the reciprocal phase vector in the phase encode direction and as a function of the reciprocal space vector in the read direction, which is the density or mobility distribution function at from a slab or a slice, okay, perpendicular slice direction at some coordinate naught, S naught, with a finite slice thickness, not very large slice, maybe a millimeter or less. And then as a function of the continuous or discrete variable RP and RR, because we have a GP which is varied from experiment to experiment and a GR which varies in each experiment. We see that the acquired two-dimensional reciprocal space signal is a two-dimensional inverse Fourier transform of the density distribution function. So if this is a direct Fourier transform of the density distribution function, we take the two-dimensional inverse Fourier transform, we get the density distribution function in 2 dimensions in a finite slab around the coordinate RS naught. And the field of view in the phase encode direction is given by this formula. Okay, 1 over the phase encode duration times the phase encode gradient amplitude increment expressed in compatible units. Phase encode gradient duration in the denominator and the phase encode gradient amplitude increment also in the denominator gives you the field of view in the phase direction. And this is the time sequence of the pulse program. You have a shaped, soft or selective pulse with a narrow bandwidth, which will excite the transverse magnetization from chosen slice, which you refocus because the soft selective pulse with a funny shape will produce dephased transverse magnetization. You rephase it by a gradient echo, reversing the slice gradient for equal but opposite amplitude and equal duration of the RF pulse duration. Okay, the duration of the rephasing gradient must match the duration of the RF pulse. But the gradient of the slice selection started and settled down before you gave the RF pulse. The start of the RF pulse is later, after the slice selection gradient was given, because the gradient requires some time to settle down. And you issue the selective RF pulse after the gradient has settled down. And so after the end of the RF pulse, you reverse the gradient to, if you had a GS amplitude here plus GS, you make it minus GS, and you keep it on for half the duration of the RF pulse. The duration of the positive lobe of the slice gradient is longer because you started it earlier before the RF pulse to allow it to settle. And then during the time that the gradient is refocusing, you start your phase encode direction in a direction perpendicular to the slice gradient. This is the phase gradient. But you have one amplitude or the other of this ladder that I'm showing here. In each experiment, use the gradient amplitude corresponding to one or the other step of this ladder. And for each of this, during that time, you also start the read gradient. There is no 180-degree pulse here. You have to keep producing gradient echoes, otherwise you won't get echoes. And you want echoes to get rid of gradient settling time problems, receiver dead time problems, to get better sensitivity. You always want echoes, but there's no 180-degree RF pulse here. So the read gradient also must be produced as a gradient echo. So you reverse the gradient first, dephase with the frequency encode and the rephase, and then you get a gradient echo. This is what you read out and you Fourier transform to get that particular function for the functional form of the signal in reciprocal space. And this signal in reciprocal space is just a Fourier transform of the density distribution function or the mobility distribution function in real space, which is what you want to get as your image. So you get that image or the density distribution or mobility distribution function by taking this measured two-dimensional data set. And if this was a Fourier transform which took you from the density distribution to the experimental data set, then you do the inverse Fourier transform to take you from the measured data set to the desired density distribution or mobility distribution function. That's what it is. And this is the experimental time sequence that you use. And the scan here in K-space, let us say here I have used a slice gradient along X, a phase gradient along Y, and a read gradient along Z. So the echo is always at the origin of coordinate space. Remember, the echo was a back-to-back pair of FIDs, and the top of the echo is like time 0. And the time 0 is like the 0 value of the K-space coordinate. So the echo top is always the origin of reciprocal space. And therefore, you can talk about parallel line scans for each value of this phase encode step ladder. You take this experiment, select the grade slice, have one particular value of the phase encode gradient amplitude, and take the readout of the signal under the gradient echo produced in the read direction. Repeat the experiment, RF excitation, slice excitation, and refocusing to produce a gradient echo slice. Then use the next amplitude of the phase encode. Read dephase and read rephase and produce the frequency encoded echo. Go back, repeat it, excite this again. Trim the slice, refocus the transverse magnetization produced from the slice. Then use the third amplitude of the phase encode gradient. Then again, produce a gradient echo for the readout and repeat this on and on. Okay, then you produce this two-dimensional data set step by step in the phase direction. Each step corresponds to this Kp naught, and you will step through the various values of Kp naught, and that is what is shown here as one line in K space parallel to the in the Z direction, which is the readout direction in this case, and then bump to the next phase gradient amplitude in the Y direction. Okay, here in this reciprocal space picture, the readout or the frequency encode data acquisition is Z direction, phase encode is along Y, and the slice gradient was along X. So in this picture, unfortunately, I've chosen a different representation. Earlier, I said the slice gradient is along Z, the phase along Y, and the readout along X. But here I've reversed the slice gradient and the read gradient directions. Now in this picture, the readout is along Z, the slice is along X, but the phase is still along Y. And so you introduce line scans in K space. And now you see, you can get, by a uniform digitization of the signal, you have a uniform sampling of the signal in K space. So there is no artifacts as you produce in radial scans, which forces you to do interpolation of the data to get rid of signal artifacts. Okay, I will not have the time to go into all this. You can do two-dimensional or three-dimensional imaging. For three-dimensional imaging, all you do this is no slice selection gradient. For a three-dimensional image, use an excitation pulse in the absence of a gradient. So the excitation pulse can, you know, excite the spins from all over the object. You're not selecting a slab or a slice now. You are hopefully able to cover the resonance frequencies of the spins across the whole object. In the absence of the gradient, that is possible. And then you start using two independently incrementable phase encode gradients along two orthogonal directions, and then produce the gradient echo in the third orthogonal direction by a reverse gradient followed by the uh, rephasing frequency encode gradient. So you can produce, when you do a three-dimensional Fourier transform of this data set, okay, you will now get the three-dimensional image. Straightforward. Two independently incrementable phase encode gradients along the two orthogonal phase encode directions, and then the gradient echo produced along the third orthogonal direction. There is no slice selection here, and you get a 3D image. And therefore, you don't have a slice gradient. You don't have to worry about the reversal of the slice gradient and so on. It's only for the frequency encode that you got to worry about pre-dephase by reversing the slice gradient and then rephase. Okay, so we will not have the chance to go through some of this other stuff. And here, important parameters in gradient echo imaging sequence. The gradient echo imaging can be very fast. You don't use 90-degree pulses for bringing the magnetization of the spin ensemble into the transverse plane. You may use a 10-degree or a 15-degree or a 30-degree or a 40-degree pulse. How much magnetization of the spin ensemble is brought into the transverse plane? M naught is the equilibrium magnetization of the spin ensemble along the direction of B naught, which is Z. And the magnetization component of the transverse plane is M naught times sine alpha. So if the pulse has a flip angle alpha equals pi by 2, sine alpha is equal to 1. So the transverse magnetization has the maximum value m naught times the sine of the flip angle alpha. Okay. So that maximum arises when sine alpha equals 1, which means alpha has to be pi by 2. But the problem is, once you have brought the magnetization completely into the transverse plane, you cannot repeat the excitation fast from the same slab, because now the magnetization is in the transverse plane. It has to go back to equilibrium with the T1 and the T2 star, and ultimately the T2 processes also. And T1 is usually very slow. T2 star is the fastest, shortest time. T2 is a little longer. T1 can be more, still longer. Unless the magnetization recovers to its equilibrium value, the next excitation will not fetch you a signal again. And you want to go step by step up the rung of the ladder of the phase encode gradients. How do you do it step by step, except by repeating the excitation and phase encoding? But to repeat the excitation, you got to wait. And the waiting time is governed by T2 star and by T2. And the longest of this waiting time is ultimately governed by T1. And to reduce this waiting time, you use a reduced flip angle. And you use an optimal flip angle alpha. And this is governed by roughly the cosine of the optimal flip angle of your excitation pulse is roughly given by exponential of minus the repetition time TR divided by T1, which is the longitudinal relaxation time along the magnetic field direction. So the optimal flip angle you use, alpha, is governed by this rough equation, and the parameters that control the optimal value of alpha is what is the repetition time do you want? Do you want to repeat this every 5 milliseconds or every 50 milliseconds or every 500 milliseconds? As your repetition time TR gets longer and longer, T1 is fixed. So as it gets longer and longer with the TR, the magnetization would have recovered towards equilibrium more and more. So you can excite the magnetization with a larger and larger flip angle, reaching the optimum when TR is like 5 times T1. exponential minus 5 is as good as 0. And therefore, the cosine of the flip angle is tending to 0, which means the flip angle is pi by 2. So you see, you can use a 90-degree flip angle if your repetition time of the sequence repetition or the pulse sequence excitation repetition is 5 times or still longer than T1. But if you want it very short, less than 3 times T1, 100 milliseconds, 10 milliseconds, well, then you have to compromise, and alpha might end up being 5 degrees, 10 degrees, 20 degrees, and so on. So this is the optimum flip angle alpha, governed by the T1 of the spin magnetization along the Z direction and the repetition time to repeat the sequence, which is up to you. Okay, and the gradient echo, total echo 2D imaging time under the gradient echo mode is given by the number of phase encode increments times the number of averages. You may not get enough signal with a single pass for a fixed phase gradient amplitude. You may want to repeat and average the signal. Okay, and you have to have TR between every pass. And so the time for each phase encode gradient amplitude to get enough signal will be NA times TR. The acquisition time, repetition time, the time between successive commencement of the slice gradient. That is TR. The time between the commencement of the slice gradient on successive scans. So you look at this 2D. So you start here, the commencement of the slice gradient. You finish after switching off the read gradient, allowing it to settle, and then you start again. So the time elapsed between the first start of the slice gradient on the first pass to the second pass, start of the slice gradient, is TR. And you want to repeat this maybe even for a fixed amplitude. You want to get enough signal. If the signal amplitude or the sensitivity is poor, you have to repeat this a number of times. And this is called the number of averages. So a repetition time TR times, okay, the number of averages for each phase encode gradient increment. So you have a number of phase encode gradient increments NP. So the total 2D gradient echo imaging time is NP, which is the number of phase encode gradient increments, times NA, which is the number of averages of the signal for a fixed phase encode value, times the repetition time of the sequence of pulses, which is like the time elapsed between successive starts of the slice gradient. So this governs the echo imaging time of the 2D gradient echo sequence, NP times NA times TR. And the fastest you can do here with the gradient echo imaging is something between 130 to 150 milliseconds. Now, I'm not going to, and the contrast in these images of 2D gradient echoes is governed by T2 star. So this is good for anything like a bold contrast as a cardiac imaging contrast, which is governed by T2 star due to susceptibility differences in different regions of the anatomical structure that you're trying to image. Okay, a bone will have a different magnetic susceptibility as compared to a blood vessel, as compared to a tissue, as compared to just bulk water. And this will give rise to differences in the T2 star in these different regions. Water T2 star in the neighborhood of a bone, in the neighborhood of a tissue or attached to a tissue, in the neighborhood of a blood vessel, and in the bulk phase, they're all going to be different T2 star. And this contrast will allow you to see in the image, where is the bone? Where is the blood vessel? Where is the tissue? And where is the intertissue, interstitial region? Okay, so T2 star can be very important, and the gradient echo allows you to do this, particularly useful for cardiac imaging and for functional MRI. And it is fast. It can be 130 to 150 milliseconds. So in 1 second, you can obtain maybe about 7 or 8 frames. Okay, so even 7 or 8 frames of a beating heart, you can capture it. But then you do this echoplanar imaging, which is a single scan raster in 2-dimensional K-space or 3-dimensional K-space. You see in the slice, you have the slice selective pulse under the slice selection gradient, which is then rephased to produce a gradient echo in phase transverse magnetization. You start the phase encode gradient, the read gradient, read gradient here is along y, and okay, and the slice is along z. And this is the picture that I showed you, okay, and the x is the phase encode. And the read is along y. Phase encode is along x, the read is along y, the slice is along z. So you pick up the slice in a plane parallel to xy by the z gradient. Then you give some positive value of the gradient, then produce a gradient echo and acquire the gradient echo during the gradient rephasing by the negative y gradient. Then switch it again, make it a positive gradient, get the gradient echo, because now you have reverse gradients, you get gradient echo. Every time you reverse the gradient, you get gradient echoes. So you get a whole series of gradient echoes. Each time the gradient in the read direction is switched, and by the time it goes through the zero, around at zero crossing, you give the phase gradient, take it to a certain value. Okay? Every time the read gradient goes through the zero crossing in successive oscillations or switchings, you give a blip of the phase gradient, and you collect the whole series of echoes. And now it's an echoplanar imaging. It's called the echoplanar imaging for 2D. You get a series of echoes from the plane. If you've done a slice selection, it's called echoplanar imaging, and you are blipping, giving short phase gradient pulses. So it's called the blipped echoplanar imaging, and this is the raster through K-space. You can cover all the 4 quadrants of the YZ plane in this case. Okay, corresponding to this, I should say the XY plane, because the phase is along X, the read is along Y. So the reciprocal space XY plane can be covered. Here I'm showing it covering 2 quadrants, but I can cover all the 4 quadrants by starting with negative values of all the gradients and taking them through zero, which is the top of the gradient echo, and taking to the extreme positive value. So you can cover all the 4 quadrants of K-space in one raster in this 2-dimensional, or if you don't do a slice selection, you use 2 phase gradients in orthogonal directions, you can cover the 3D. So this can then do a 2D image in 30 to 50 milliseconds. A single blipped EPI measurement with a 2-dimensional raster covering all the 4 quadrants of the KX, KY plane or the read phase plane in the reciprocal space can be covered in 30, 40, 50 milliseconds, which is therefore about 4 times faster than the ordinary gradient echo. These are also gradient echoes, but you have a whole train or a series of gradient echoes, and the corresponding reciprocal space trajectory is the zigzag, where you get the echo, take the phase gradient to the next value, get the echo in the opposite direction, traversing the K-space in the read direction in opposite sense, take the phase echo to the next value, traverse it in the opposite direction, and so on. But you see, successive traverse in the read direction have opposite sense. That is the problem with echoplanar imaging, that the K-space trajectory in successive scans in the read direction is opposite. So you got to worry about this. This will reverse the image in that read direction because of the Fourier scaling theorem. You know that little f of t, if it has a Fourier transform capital F of omega, then the scaling theorem of Fourier transform theory tells you that little f of at, where a is a scaling parameter, has a Fourier transform 1 over mod a times the capital F frequency function of omega by a. And if you are just reversing the traverse, that is like the scale parameter a is -1. So the Fourier transform of the successive scans in the echoplanar imaging, which are in opposite directions of the read K direction, okay, they will correspond to a is equal to -1, and that will just give you if the forward direction gives you the f of omega, now you'll get f of minus omega. So the image gets reversed every alternate scan. Okay, so that's what I put down here. So what you have to do is, that will just completely mess up your image. So you have to pick out the alternate scans. Let's say you always want to retain only the left to right read scans. But every successive scan will be left to right, followed by right to left, followed by left to right, followed by right to left, and so on. So you pick out, let's say, the odd number scans, they're going from left to right. separate out the even numbered scans which are going from right to left, then reverse those data in case space or in time domain, and then put them back. Now you have got all the read frequency encode scans going in the same direction in successive case space line scans. Then you will get an undistorted image. Okay, so processing requires all of this, and you got to have a very good magnetic field homogeneity, because gradient echo sequences which produce a train of gradient echoes are notorious for the artifacts they produce in the images due to poor magnetic field homogeneity. You have to have excellent gradient hardware which can switch very fast, which have a good pre-emphasis and eddy current compensation, actively shielded gradients. Okay, and then with fast switching, you also have to have excellent magnetic field homogeneity, excellent magnetic gradient switching times, and field and gradient shielding. Only then the EPI will do well. But that is what is required to produce fMRI and cardiac images. The other way of producing echoes is by spin echo using 180-degree pulses. I will not talk about this. This is easy to do. It is good to avoid susceptibility issues in your image. Sometimes you will have susceptibility issues, magnetic field inhomogeneity, RF inhomogeneity issues, which are not related to the structure or physiology of the object that you're trying to image. And you don't want these susceptibility or imperfection based artifacts in your images. In that case, you use a 180-degree RF pulse following the excitation, and you pick up the spin echo. This is not a gradient echo now. Okay, you may still do a slice selection, but then you use a 180-degree RF pulse. There is no gradient echo for slice selection, and you get a spin echo. This is slow. It could be 3 to 10 times slower to produce a spin echo based two-dimensional image as compared to even a gradient echo image, and maybe 10 to 30 times slower than an echoplanar image. But it is free of susceptibility artifacts and relatively free of imperfections in the hardware. RF imperfections or magnetic field inhomogeneity imperfections. That is a spin echo. So, that's how it works. We will not go into the details, how to produce spin echoes, how to produce gradient echoes, and so on. And I will just skip all of this. One thing you have to worry about is the fat water discrimination in MRI. I'm afraid I have no time now. I have tried your patience long enough, and I'm going to stop now because I think I have exceeded by half an hour. So I'm going to stop now. And finally, the encoding of motions, which I mentioned, I just show you for MR angiography. This is the kind of gradient waveform that you use. Okay, for the phase encode, for example. Earlier, we showed the gradient as having just a positive lobe, and then you step it up from negative to positive in successive scans. But if you use a bipolar gradient, every pass has the bipolar gradient, then this will only image moving spins, because the integral over this gradient waveform as a function of time is 0. So if you look at the Taylor series expansion, when the integral of the gradient over the time is 0, then static spins will not be imaged. In the Taylor series of the expansion of the motion, the 0th order term is just the static position of the spin or the molecule. The first order term is the constant velocity term. The second order term in the expansion is the constant acceleration term, and so on. So with this kind of bipolar gradient, whose time integral is 0, the static spin contribution to the image is vanishing. You will pick up the constant velocity term. With this kind of a gradient, reverse bipolar gradient, the static spin contribution to the image is annulled. The constant flow velocity spin's contribution to the image is annulled. You will pick up the constant acceleration flow image of the spins which have a constant acceleration. In an image produced with this gradient waveform, you will not see the static spins in your image. You will not see the spins which are flowing with constant velocity in your image. You only see, to lowest order, the spins which have constant acceleration. in an image produced with that gradient waveform, you will not see the static spins. You will see to the lowest order the spins which have a constant flow velocity. Okay, this is how you can do magnetic resonance angiography. I have now completed my presentation after having exceeded my time by at least half an hour. Thank you for your patience. I will be very happy to answer questions if your organizers will give you the time to post your questions. Thank you.
Sure, sir. Thank you, sir.
Good morning, sir.
Yeah.
This is, we have a small message for you instead of question. Dr. Jayavel posted a comment in our live YouTube channel to convey this message to you.
Yeah.
His message is like, thank you for organizing this talk. A great teacher, researcher, fortunate to learn a MRI.
Sorry,
from...
sir, I
Yes,
did
sir.
not hear you properly. Can you please repeat it?
Sir, Dr. Jayavel posted a comment in a live YouTube channel,
Yes.
sir. So
Yes.
we have,
Yeah.
so he wants to convey his message to you.
Yeah.
His message was, thanks for organizing this talk. A great teacher, researcher, fortunate to learn a MRI concept from him during a UG chemistry minor course in IIT. Very humble teacher. He wants to wishes you many more lectures to come, and so he just want to convey his message to you.
Oh,
sir.
thank you so much. This was Dr. Jayavel, is it?
Yes, sir. Yes, sir. Jayavel,
Thank you
Dr.
so
Jayavel.
much, Dr. Jayavel. That's extremely kind and generous of you. Thank you.
Yes, sir. Yes, sir. Participants, any queries you can ask.
Yeah,
Chandrakumar,
please.
sir.
Sir, excuse me, sir. I am Sudha.
Yeah.
Sir, I want to know what are the risks of MRI when he or she undergo MRI test.
Sorry, madam, what is the use of MRI when?
Risk of MRI.
Oh, risk of MRI.
Right.
You see, the risk of MRI, typically, there can be two different risks. One is related to the radio frequency heating.
Yes, sir.
So FDA, for example, prescribes a specific absorption rate limit of how many watts of radio frequency power can be deposited per unit tissue mass at a given radio frequency wavelength or radio frequency, okay, RF frequency.
Okay, sir.
So you have to ensure that the RF wattage over your experiment will be within the SAR, specific absorption rate limits. Otherwise, like the microwave oven, you can end up cooking the tissue.
Yes, sir. Yes.
Okay, so one hazard is to be sure that the RF wattage and the power deposition at your given RF frequency is within the FDA prescribed SAR limits. Okay? But this is not difficult to do. It is with the SAR limits being satisfied that we can do EPI or gradient echo images or spin echo images, where you typically have one radio frequency pulse every 10 milliseconds will be the shortest, or every millisecond, let's say every 10 milliseconds. Okay, so the power of the RF may be a kilowatt, but it is on maybe typically for 1 millisecond, and then you have 10 milliseconds or more of off time. So you can see that the power deposited will be a fraction of a kilowatt. It will be a few watts. And as long as you stay within the SAR prescribed limit for biomedical MRI, you're safe. That is one. The second thing is related to the magnetic field gradient switching. Now, the magnetic field gradient switching, if you make a high slew rate of the magnetic field gradient switching, then some people report a tingling effect in their spine. And therefore, you have to be sure that the gradient slew rate or the gradient switching time is kept to a comfortably low value so that people don't result this kind of giddiness or tingling of the spinal cord. But usually a gradient switching time of the order of a millisecond is usually without any trouble in the perception. So the real physical trouble is with the RF heating. Stay within the specific absorption rate stipulations. There's no trouble with that. And the perceived tingling of the spinal cord is just a perception. It is not a physical hazard as far as I know. But if you have a modest slew rate of the gradient switching, that is also okay. If you have 1 millisecond gradient switching time, for example. The third is a claustrophobic sensation because you're lying in a magnet, you're lying in a magnet which is like a large pipe. இந்த வீராணம் குழாய்னு நம்ம சொல்லுவோம் இல்லையா, அந்த காலத்தில் வீரநாராயணபுரத்துலேருந்து கடலூர் பக்கத்துலேருந்து ஏரி தண்ணீரை சென்னைக்கு கொண்டு வரதுக்கு இந்த பெரிய பைப்ஸ் பதிக்காம ரோட்லலாம் போட்டு வச்சுருந்தாங்க பத்தாண்டுகள் கணக்கில். இப்போ அதெல்லாம் காணாமல் போயிடுச்சு, பதிச்சிட்டாங்க போல இருக்க ஒரு பகுதி. வீராணம் குழாயில் படுத்துட்டு இருக்கிற மாதிரி இருக்கும். So some people feel claustrophobic. But these are perception issues, they are not physical hazards. So these are the three discomforts that people can have. One is a physical hazard of RF heating, which you avoid by ensuring that the wattage of RF power at your chosen resonance frequency is less than the SAR specified limit. The second is that the gradient slew rate is comfortably slow. That's a perception problem. 1 millisecond switching time is usually all right. And the third is some people feel claustrophobic. அதுக்கு என்ன பண்ண முடியும்னு எனக்கு தெரியாது. Some people talk about inside out magnetic fields. இந்த மாதிரி இந்தியாவில் MRI scanners வந்துருச்சான்னு தெரியல. But in principle, the technology has been available in some places abroad where the magnetic field is an inside out. So the object to be imaged is not placed inside the magnet. அந்த மாதிரி inside out magnetic field இருக்குன்னாக்கா you can get rid of the claustrophobic feeling also, which is however only a perception problem. But inside out magnetic fields நம்ம நாட்டில் MRI scanners இருக்கான்னு எனக்கு தெரியல. Maybe others who are actually working in clinical installations may be able to tell me. I don't know where Dr. Jayavel, for example, is working. He didn't tell me that. But if he is working with a imaging company like GE or Philips or in a clinic where MRI scans are done, maybe he can add to this about whether there are inside out magnetic field scanners in India. But such designs are available.
Okay. Okay, sir. Thank you, sir. Thank you, sir.
Welcome.
Sir, hello.
Yeah.
Hello.
Yeah.
Hi, sir. Different.
Hello.
Hello.
Yes. Speak on. I'm listening.
Sir, one more question from Rangaraj Bhattacharya.
Yeah.
Sir, T1 imaging, 63% of magnetization will be required, and for T2 imaging, 37%. How T2 decay occurs quickly?
No, can you please repeat that? I heard something about 37% and something about 63% for the T2 and the T1. Can you repeat the question?
T1 imaging, 63% of magnetization will be required, and for T2 imaging, 37%.
No. You see, if you look at the equations that give you the magnetization as a function of the recovery time, okay? If you have inverted the magnetization with the 180-degree pulse and you're waiting some time before sampling the magnetization with the 90-degree pulse, then the inversion recovery period, the magnetization as a function of the recovery time goes as m0 into 1 minus e to the power minus TR by T1. Okay, so that is the functional form of the inversion recovery. The magnetization at time TR is given as m0 into 1 minus e to the minus TR by T1. So if you wait long enough, you can even get back 100% of the magnetization. But of course, you don't want to wait long enough. So it is just from that functional form of the recovery equation. I don't know whether I should share the screen again and see whether I can quickly go to that slide. Can I try to do that?
Yes, sir, yes, sir. Sure, sir.
Let me see, share screen. Um, okay, now just give me a minute.
Yes, sir.
Yeah, you see, you have these differential equations for the Z component of magnetization and for the X or the Y component of magnetization. Depending on the initial condition, mz at time 0 or mx at time 0, which is the start of the experiment, or my at time 0, you integrate these differential equations, then you will see what is this 37% and 60. Look at this transverse magnetization. My at a time t, if at time 0 you had the transverse magnetization of magnitude m naught. Okay, now you can see this. At a time t after the excitation pulse, you produced immediately after the excitation pulse the Y magnetization, and at a time t after the excitation pulses, the Y magnetization is its initial value, which is its equilibrium value, all rotated in the transverse plane, multiplied by this decaying function. And if you look at this decaying function, e to the minus t2 by t2 star, this is why you talk about this 37% or whatever. Okay, for the transverse magnetization. For the longitudinal magnetization, you have to integrate the other equation. dmz by dt is equal to minus mz minus m naught by t1. And if you integrate that, you will see that mz as a function of time is either m naught into 1 minus 2 times e to the minus tr by t1 for inversion recovery, or for saturation recovery, mz at a time t is m naught into 1 minus, not 2 times, but 1 times e to the minus tr by t1. Hence, you get this 63% or whatever. So that's really up to you. It all is a function of tr. But basically, that is how these exponential functions behave. Okay, I hope that answers your question. Just use these differential equations, integrate them for given initial conditions, and then you know what we are talking about. Okay, if you have further issues about that, you can email me or you can talk to me on WhatsApp or whatever. I think the organizers have my email ID, my WhatsApp and mobile number, and we can discuss it in more detail. But basically, this kind of percentage, 37% or 63% and so on, basically is related to the recovery of the transverse or the longitudinal magnetization. Okay, how much transverse magnetization is left or how much longitudinal magnetization is recovered.
So one more question from Smita ma'am. Why still research becomes challenging in improving the resolution of an image in MRI?
Sorry, madam, why what becomes challenging?
Improving the resolution of an image in an MRI.
Yeah, because you see, the magnetization of nuclei is very weak. That is the reason.
Okay.
Okay, because the magnetization is very weak. Okay, you know, what is the energy quantum of these radio frequency waves that we are talking about?
Yes.
They are 1 over 10,000 of the energy of thermal fluctuations. Okay, energy of thermal fluctuations is kT, no?
Yes.
The noise voltage is like kT square root of kT, right?
Yes.
The noise voltage is square root of kT. The energy of thermal fluctuations kT. And as compared to kT, okay, if kT is like 200 inverse centimeter, then the energy of the RF quantum that we use for MRI is like 0.01 inverse centimeter.
Okay.
So we are talking of a ratio of the energy quantum that we use for MRI as compared to the thermal fluctuation energy quantum. This ratio is like 10 raised to the -4. And therefore, your signal sensitivity or signal to noise ratio is extremely poor. And the resolution is limited by the sensitivity that you can get from a picture element pixel or a volume element voxel. And so ultimately, that's where it goes. The resolution is always challenging because the magnetization of the nuclei is so weak, utterly weak. And even after amplifying by millionfold by the resonance process, it is still so weak that the signal voltage is hardly of the order of millivolts, if not as bad as microvolts. So it is always fighting against noise. And the signal to noise determines the resolution also. We gave a number of factors that limit the resolution. The motion of molecules or the self-diffusion of molecules. The gradient amplitude you can use to differentiate one volume element or one pixel element from the other in the image. How much gradient you use. Okay, the field of view, those formula give you that. But the fundamental limitations, as opposed to the technological limitations, the fundamental limitations, diffusion, and the basic technological limitation and fundamental limitation, both is this signal to noise ratio or the sensitivity. And the other technological limitation, purely technological, is gradient. So all these three things limit the resolution. But at the same time, for MRI based on proton nuclei, madam, in practice, I don't believe it is a severe limitation. For most standard clinical purposes, the resolution you can obtain is adequate for a short enough imaging time. It is when you want some ultra special effects to be properly imaged and captured, which are fast processes, faster than the beating heart. Okay, if you want to make a movie of the cardiac cycle, now, roughly you can say you have a pulse per second. So even if you are able to capture a 130 millisecond 2D image, you can capture only 8 frames per second. So you can capture only 8 frames of the cardiac cycle. But if you do that is with the 2-dimensional gradient echo imaging. But if you do an echoplanar imaging, maybe you can capture between 30 to 40 or 20 to 40 frames in the cardiac imaging. You can combine these frames in the software as a cine kind of a movie. And you can see the beating heart. For many purposes, this is good enough. But if you have cardiac arrhythmia, if you have some processes which are much faster than this 25-30 milliseconds, then you have a problem.
Okay.
Then there are these fundamental limitations. Now, you want some image resolution. If you reduce the number of phase encode steps, you can do a faster image. But if you reduce the number of phase encode steps, then you have to worry about the field of view that you will cover and the field of view as well as the image resolution. So there are compromises and trade-offs. Okay, if you have the same number of phase encode steps but increased increments, then the field of view is going to get reduced. Okay, if you keep the same step size in the phase encode direction but reduce the number of steps that you have, then the resolution in the phase encode direction is reduced, but the time is also reduced. So there are various trade-offs. But yes, you have limitations on resolution. For very fast phenomena, it will hit you hard. But for standard phenomena, I think in the clinical context, it's usually sensibly fast. But yes, the sensitivity, in summary, in addition to the motion by diffusion of molecules and in addition to the gradient amplitudes technologically available, but above all by the sensitivity, the resolution is limited. But you can make a variety of trade-offs gain something at the expense of something else, and so on, and try to pick out the specific information that is of great relevance for you, sacrificing something else. So the great thing about MRI is it has this flexibility. You can play a lot of trade-off games. But yes, the imaging time and the imaging resolution and the imaging sensitivity, yeah, this is always a bugbear. So there are methods. We talk about some methods of hyperpolarization, where we add, let's say, a free radical or a polarized spin state by an electronic excitation. Let's say hyperpolarized xenon, hyperpolarized helium, to image blood with hyperpolarized xenon, or to image lungs with hyperpolarized helium. And these are hyperpolarized by exciting an electronic transition of rubidium atoms, let us say. And then you can improve the sensitivity by a factor of 100 to 10,000. And then you can get better resolution. But then the problem is that the hyperpolarization will die quickly over a time of the order of T1, the longitudinal relaxation time. So again, you have to worry about trade-offs. Supposing your T1, after hyperpolarization, you have a T1 of the order of 1 second. Now, your frame takes, let us say, 50 milliseconds if it is EPI. You can get only 20 frames in 1 second. So again, you have to worry about trade-offs if you want many more frames, okay, to get a better time resolution in spite of hyperpolarization, because the polarization will have a decay time. So it is all a matter of fine-tuning horses for the courses. And this is where magnetic resonance is, on the one hand, extremely flexible, extremely rewarding, but on the other hand, it is extremely challenging. If the radiologist doesn't have a grip of exactly what they are doing, because there are so many implicit things which in the typical radiological training, if you're not a specialist in magnetic resonance, you may or may not appreciate as a typical part of the radiological training. Then it can trip you up. But please remember this is the flexibility and the rewards on the one hand, and the challenges and the pitfalls on the other hand, of anything to do with magnetic resonance and MRI. Very flexible. Anything is somehow possible if you are inventive enough. But if you do it wrong, you got hell to pay. Totally misleading output and information. But yeah, there are barriers, but there are also attempts to overcome the barriers. Then you have further barriers you overcome, and then it goes on. And this is a great thing for those of us in magnetic resonance. We feel blessed. We feel blessed, even those of us who don't do biomedical work. There's so much challenge and reward, and applying your mind which is involved, so much challenge which you enjoy. This is the blessing of magnetic resonance, if I may put it that way. Okay. I hope I gave you a sense of the answer to your question. Any and all of you who wish to strike up a further conversation or a dialogue with me, please feel free to correspond with me by email, by WhatsApp, by phone call, whatever. Okay, anything. I'm at at a mutually convenient time, we can always discuss. I suspect that Dr. Jaival is probably from IIT. That's why
Yes,
probably
sir.
he also said
Yes,
that
sir.
he had attended the
He's
course.
a
Yeah,
student.
I can identify him now.
Yes,
I was
sir.
not sure, but then this remark he made that he had attended the course put me wise to it finally. I'm usually like a little bit slow on the uptake.
Yes, sir. Yes, sir. Sure.
Okay, any other questions?
Thank you, sir.
No, sir.
Nothing, sir.
All right, but again, any of you are welcome to strike up any further dialogue with me, conversation with me, which you may be interested in. You're welcome. And at our mutual convenience, we can hold such a dialogue across email, across some kind of chat or Skype or whatever, WhatsApp or email. Yeah.
Sure.
Thank you. Sudha ma'am, shall I?
Start your thought.
Yes,
Thank you.
good afternoon, friends. Myself, K. Pradeep, Assistant Professor, Biomedical Engineering Department, PS and CET, It is indeed a great pleasure for me to propose a vote of thanks for this session. On behalf of Department of Biomedical Engineering, faculty, students, PSN CET, I'd like to thank Dr. N. Chandrakumar sir, Professor, Department of Chemistry, IIT Chennai. Today's topic, Principles and Applications of Magnetic Resonance Imaging, was very relevant to the objective of this Sttp, where image acquisition happens with MRI for disease diagnosis. Sir, you are the pioneer in NMR and MRI. We know that you was the one of the first person to set up the MRI lab in India. Sir, you like a hydrogen atom which aligned during the MRI process with magnet. We participants also very much attracted by your presentation today. It's great pleasure to have a great personality like you for this session. Thank you, sir, for your presence online and your in your lecture during your busy schedule. So thank you, participants, for spending your valuable time for learning process, even in this Boxing Day. Thank you all for your presence. The next session will start shortly. We'll have a short break.
Thank you for your kind remarks,
Thank
and
you.
it has been a pleasure participating from my side.
Thank you, sir.
Thank you, sir. Thank you very much, sir.
Welcome.
Dear participants, we'll meet you at 1:30 p.m. After that, you have two sessions from 1:30 to 2:30 one session and 2:30 to 3. We'll stick on that time. Okay, so you have 1 hour lunch break. So we will meet you again at 1:30 p.m. Thank you. Thank you, participants. And you, the feedback for this session is posted here. Okay. So you fill up and go for a break. I will meet you at 1:30. Thank you.